So if there is any new teacher who is joining, please check the link on your WhatsApp and try to fill that survey. But just don't talk with each other about any of these answers. Just do it by yourself so that we get independent sampling. Thanks.
Hi.
Hey Neeraj, hi. Is Aniket there with you?
No. Aniket is in Bombay, no? I'm in Bangalore.
Okay. I see. I thought with this Mysuru workshop going on, whether you are in.
No, that's Science Day on Sunday. I'm not.
Okay, of course. I have dropped a message to Aniket and Neeraj. Just to give a background, we are doing a pre-survey and a post-survey just to understand the
I
efficacy
saw
of the
that.
workshop.
I saw that.
Yeah. So we have asked, since we were waiting anyway, we asked the teachers to fill it up.
Mm-hmm.
Aniket has not yet joined, so I am messaging him. He has not, he's not responding. Maybe he is busy somewhere. So
Let me try to call him. Just give me just like 1 minute or so.
Yeah, please.
Okay, I guess we can get started then. If
Yeah.
yeah, no problem.
So we will just wait for some 5 more minutes. Let them finish off, and then I.
Okay, sure. Yeah. Please, no problem.
Uh, 29 has registered, and I think 19 are there. So let us see. Somebody may come late also.
Yeah, sure. You can ask them to fill the survey anyway.
Yeah.
And we have posted it on the group, so hopefully some of them will do it, even if they are not attending. Yeah. Yeah, we also just finished a workshop in Pune, so.
Yeah. After this initial inauguration, we will all stand with online and offline participants together, means all of us, and we will take a group photo because let us take it now itself.
Sure. So I'm seeing the responses trickle in, so very good. Thank you so much. A few more remaining. Yeah.
So I think all of you are over, done with? Anybody still doing? Brilliant. While the inaugural session, I think you can rotate the camera towards the photo. Not now, when we start.
So, Neeraj, I will send you some snapshot of the results so that you can take a look and
Yeah.
see where to pitch and how to pitch. Yeah.
Sure.
मेरा ग्रुप में होगा आगे in the group already joined the group one WhatsApp group and you can just join. Maybe can you just help them to join the group? It is in your mail. You have sent a confirmation mail. In that mail, the group just join. So now we will start this thing. So yeah, so let me just give a formal introduction to this program. So Regional Science Center and Planetarium in collaboration with International Astronomy Union's Astronomical Union Office of Astronomy in India Center, is organizing this TTP program for 3 days. Now, these types of programs are organized or will be organized throughout the country. And the purpose of these programs are actually to proliferate these teaching learning process of astronomy among school children. Because many syllabuses have already taken out the astronomy portion and it is in very rudimentary stage. But it is felt that the progress in astronomy has gone to such an extent that we should actually have our kids knowledge of astronomy. The way it has to be taught, the way the conceptual things can be taught in a very lucid way, these things are actually what we are trying to focus in this workshop. It's not a workshop, it's a great deliberation on great research work in astronomy. So many things will be told, but mainly pedagogical aspect, how to teach students the concepts, how to make demonstrations, how to make models, and the best way, best practices for using all those things. That will be other part of the focus here. So we have with us Dr. Sundu, who is professor in India University Center of Astronomy and Astrophysics, Pune. He is also the manager of Office of Astronomy in India Center. And we have Dr. Niruj Mohan Raman, who is actually the national and national or regional, I think education.
Astronomy education coordinator.
Regional.
Astronomy education coordinator, and who is a professor in Indian Institute of Astrophysics. So he will be taking the first talk. In fact, in your file we have given a booklet called Great Ideas or Big Ideas in Astronomy. So that booklet is brought out by Office of Astronomy Education International. So he will be explaining something related to that and his own ideas also about how to explain the new findings of astronomy in a better way to the students and what are those findings. So we also have with us our project coordinator Balaji, Balaji, who is also in this center and in this center, and he will be speaking about the our mode of objective of this existence of this center. We have been surviving here for last 27 years with a lot of programs. In fact, at IUCA also we have been previously program on sun and solar astronomy, and he was the person who coordinated our professor who was there. I think who is in the committee. Anyway, I'm forgetting his name. So we have been in touch and we have done a lot of programs together. So I request Balaji sir to come and give formal welcome.
Morning to all teachers, to all the participants of this program, and the members from IE office. This program, as my colleague said, it is a collaborative program of Regional Science Center and Planetarium, as well as International Astronomical Union and Office of Astronomy Education in India. And like these kind of programs, we used to conduct, organize many at Regional Science Center, and we are here for more than 27 years. And I think such kind of teacher training program, especially, we used to do to introduce change. Change means the teaching should not be like whatever is there in the textbook, something has been taught and they will write, and at the end of the academic year they will write the examination and they will finish the course. But what is the knowledge they are gaining, that is more important than the marks. Marks is only on the paper, but what is there in the mind. And as we all know, when we do something, means by doing some activity or by doing some experiment, or you will understand the topic or concept better, especially when it comes to science or astronomy or technology. So with this motive only, we used to conduct hands-on experiments during even in this 3-day workshop also, you will find more activities compared to the lectures. Because you have to do on your own some kind of whether you can say kit or a model, whatever it is. And this you have to carry to your school so that the group of students or the whole school can practice this kind of activity or kit, and so that they will learn astronomy. Particularly after this program, they will learn astronomy more effectively. And you know, Kerala is always first when it comes to science education, and you know the first astronomy club, the Kerala School of Astronomy and Mathematics, was established in I think 14th or 15th century. It is the first of its kind in India. So that means astronomy education has started well before our ancestors have started, and it's not only on astronomy, it is on mathematics also, and the legacy is continued, and even with the support of state government, we have been established a planetarium here, and this planetarium, you all know, is very popular in this Malabar region, and every year we are getting more than 5 lakh visitors. So once again, without wasting much time, I thank the collaborators for choosing Regional Science Center Calicut for this wonderful program, and I wish you all the best.
Thank you. So I request Professor Sudhir to give a formal inaugurated.
Yeah, sure. So, hello everyone. I'm Surut Bore, and I'm basically the manager of the Office of Astronomy for Education Center India. This particular office was set up under the auspices of the International Astronomical Union, which is a union of professional astronomers, and they have prepared a head office in order to use astronomy in order to introduce science education to school students. And that's the reason why this Office of Astronomy for Education was set up. So I'll give you a brief overview of what we do, who we are. So this particular OE Center India, it was established in February 2022. It's a joint collaboration between the Inter-University Center for Astronomy and Astrophysics, AYUCA, and TIFR Homi Bhabha Center for Science Education. We also collaborate with many different institutes within India, and the Indian Institute of Astrophysics is one of the MOU signatories on this. And Neeraj, of course, is at IIA, who has been helping us out with some of these activities. Here are the people involved. We are a small team, but with the help of many of you, I think we can grow together and then help to take astronomy to the school students, and then proliferate the use of astronomy in order to attract students for science education. So here are the main activities of the OE Center India. We would like to professionalize astronomy education. We would like to provide access to good resources. We would also like to promote astronomy in curricula, just as Jan said, that the number of astronomy topics itself is reducing in curricula, so we would like to promote that. And finally, we would like to create and nurture this network of astronomy associates who can do all these tasks. So in order to professionalize astronomy education, we have been conducting and organizing these teacher training programs. So we have funded 3 different programs within this financial year. The first of these happened at Kolkata. You can see all the happy faces here, and I'm sure that we will get one more such picture from you soon. This happened in December. Then we have wrapped up in February. There was one workshop which was held just over the weekend, so Friday and Saturday at AYUCA. And then, of course, you are attending this workshop at the Regional Science Center in Calicut right now. In addition to this, we also provide access to good resources. You can see multiple different resources that we have made available here. Together with the Astronomical Society of India, we have worked on a booklet called this regarding the Savai Jai Singh's Jantar Mantar observatories. And this particular booklet was translated into 15 different Indian languages. Then the booklet that you have been given right now, this is the booklet on big ideas in astronomy. So this basically tells you what are the big ideas that we would like students to know as they grow up and go through the school curricula. Then there's a booklet on positional astronomy related to various articles that came in a magazine in TIFR. And so we collected all the astronomy articles from here and put it together in a nice graphical form so that students can read it, find it interesting, and also learn about astronomy. And then finally, there are lots of jargon which is used in astronomy, and we would like to simplify it. And so the Office of Astronomy Education has decided to take these jargons and then translate it into, or put it into words, try to explain it in simple language. So we have been using these astronomy glossary terms and trying to create a deck of astronomy cards. We would like to also translate this material into various different local languages. And for all of these things, it's not just us who can do this task. Translations involve a lot of networking, and we are hoping that some of you can also help us translate this material into the languages that you are comfortable with. So we need help in translations, and we would like you to welcome you as volunteers. So in addition to this, we also do try to promote astronomy and curricula. So for this, we try to understand what is the current status of astronomy education in India. And for this, we run different types of student questionnaires, conduct teacher interviews. One of the questionnaires that you are seeing at the beginning of this workshop is similar to the questionnaires that we give to the student. We'd like to understand their interest and perception in astronomy, their understanding of astronomy topics, desire for knowledge in how to get into astronomy, and to learn about the different concepts in astronomy. So we are doing all sorts of things in order to learn about things, where they stand, and use this knowledge in order to then promote astronomy in school curricula. Together with this, we also try to create networks. So we go in both international and national meetings. So there was the Astronomy Society of India meetings. There we held one of the workshops for outreach and education volunteers where they could communicate what are different pedagogical techniques that they have been using. We internationally network through all these centers and nodes that you are seeing, but also with the broader astronomy community, with the International Astronomical Union's General Assembly, where we also have a big presence. So we are trying to bridge these or create these networks both nationally as well as internationally, and our hope is that that helps to get astronomy as a topic for all. In case you want to reach out to us, we have a website. There are Facebook and Twitter pages that you can follow. There's an Instagram account if you are interested in that. So there are many different things that go on. So one last thing that I want to say before I end, which is the following. I mean, the role of teachers in order to get students into astronomy is really large. I myself was introduced to the joy of astronomy by a teacher, and it was her who told me about a stargazing session which I went to, and I got totally fascinated by this subject. And then overall started to connect the dots of how whatever I see in the heavens, I can learn about it by looking at the equations that are given in the textbooks, and how I can apply the knowledge that I learned in the textbooks in order to learn about things that are happening in the real life. And so that is actually the power of astronomy, that you can lure students in order to study about science and then connect the things that they learn in textbooks to science. So I feel you are the connection between astronomy and students. And you do these tasks and have been doing these tasks for many years now. So what you will learn in this workshop will be cutting edge topics in astronomy. You will learn about the basics behind these astronomy topics. and things that are taught within the schools. We hope that we can teach you or we can tell about it to you a little bit better. But then our hope is that you will be equal partners to us and help us in taking some of the complicated topics and tell us how we can teach them also to students. Okay, so you are our first line where we try to tell you what is going on in astronomy and what are the different concepts in astronomy, and we are hoping that you can translate this knowledge that you learn in to the teachings that you use in order to teach your students. So let's act as equal partners and try to get this done. So I hope you'll enjoy this workshop, and please let us know and get in touch. Thank you.
Thank you, Subodh. Now I request Dr. Niruj Mohan just address the gathering. He is the person who will be taking the first two sessions today. So that will be after our tea break. We'll have a small tea break. So before that, please address, tell something about you.
Thank you so much, Jay Rahuli, for asking me to join you. I'm really sorry I can't join you in person. I'm sitting in Bangalore and I'm doing this online talk. I'm going to talk to you for I think more than almost 2 hours after this, so I won't bore you too much right now. You'll see a lot of me after tea. My name is Neeraj. I work at the Indian Institute of Astrophysics in Bangalore. The institute itself is fairly old, depending on how you define its history. We trace its origins back to 1786, when the British started the Madras Observatory. And 1786, the Madras Observatory started in Ungampatti, and 1899 it moved to Kodaikanal in Tamil Nadu, which is now the Kodaikanal Solar Observatory, and in fact we're going to celebrate its 125th anniversary starting April. And in 1970s, it was formally established as the Indian Institute of Astrophysics under the Department of Science and Technology, Government of India. Its headquarters is in Bangalore, and we have around 50 or so scientists or astronomers or faculty members here working on every single branch of astrophysics or astronomy you can think of. We have around 70 students doing PhD with us. We have many postdoctoral fellows. We have many more engineers than we have scientists, for a very good reason. And then of course we have so many student interns, student project trainees. The reason we have so many engineers is also because we maintain 5 field stations across India, or observatories. The oldest of course being the Kodaikanal Solar Observatory. We also have an observatory in Tamil Nadu at Kavalu called the Vapu Observatory. That is somewhere, it's very close to Vaniambadi or Ambur, on the way from between Vellore and Bangalore. It was started around in the 70s, and it is an optical observatory functioning solely to look at stars and galaxies at night, as opposed to the Kodaikanal Observatory, which only observes the daytime. We also have a radio observatory in Gaurikatnur, which is 2 hours north of Bangalore here in Karnataka, which is operated along with the Raman Research Institute. And one of our pride and joy, of course, is the Indian Astronomical Observatory we had set up more than 20 years ago in a place called Hanle in Ladakh. When it was built, it was the world's highest observatory and in the middle of pretty much nowhere, so you can imagine how difficult it was to build and to run it. It has now our own telescopes plus telescopes from other Indian institutions, and many more are coming. We also run Hanle Dark Sky Reserve at the same place as well, over an area of around 1,000 square kilometers. In addition, we have a technology center in Hoskote. Hoskote is an hour and a half from where we are in Coromandel in Bangalore, and that is a center where we make instrumentation. Currently, it has a clean room where we made 2 space payloads which are in space. One is the Ultraviolet Imaging Telescope, which is on AstroSat since 8 years, and the other is the Visible Emission Link Coronagraph, which was launched on Aditya last year on 2nd September, and is going to start operation sometime this week or next week. It also has a huge center called the ITOF, which is where we're going to make instruments for what will be the world's largest optical telescope, whose mirror is going to have an aperture of diameter of 30 meters in Hawaii, and India is an equal partner in that, and we are contributing in terms of many instruments which we're going to supply from them. So that's broadly what we do. Our main focus, of course, is research as well as instrumentation and running the observatories for both our own astronomers and astronomers from across India and the world. It also has a section called Scope, which I'm head of. Scope stands for Science Communication, Public Outreach, and Education. And our ambit or our objective is to promote astronomy among the public, among the school students, teachers, etc., in Bangalore, in Karnataka, in India, and also to promote what we do across the world. And it's in this context that I'm here today. I'm very happy, like Suraj said, to see so many teachers. I looked through some of the responses you have put in, and there's a lot of many years of experience sitting in this room in front of me, and I'm very happy to have you here. And as mentioned by Suraj, astronomy is something everybody is interested in. Every school child is interested in astronomy, but then it's we leave it to them to engage in their interest completely outside the school, right? By looking at YouTube videos, going to the planetarium, asking their friends, and so on. We really do not cater to that interest in the school formally in the curriculum at all in any proper way, with notable exceptions. And many teachers repeatedly come to us and say, look, we would like to cater to the demand, but we need extra training or some support in order to do that. And I think this kind of workshop goes a long way into doing so. I also looked at responses where there were questions asked about, do you need some support in explaining certain issues? I think most of you have indicated that you would need some kind of support. And I think that's really good to hear, because that also means that you've been, there's a demand in front of you from the students, which is why you say that you want support from us. And therefore, I think this will be a very fruitful workshop. And thanks again to the Regional Science Center and Planetarium of Calicut for hosting and organizing this, along with the OAE India Center from Pune. And hope after these 3 days, there'll be at least 20 schools where astronomy will take off really well. So thank you.
Thank you. So we have also with us Aniket Sule, Dr. Aniket Sule from Homi Baba Center for Science Education. Aniket, you are there?
Yeah, I am around.
Yeah, just a minute. So I welcome you to this inaugural session. I would request you to say a few words about astronomy education and role of school teachers in astronomy education, and what is the intention of this workshop as per your views. And please.
Thank you, Jayant. Sorry for the delay. I could not join on time. So I missed what Surud said and mostly what Neeraj said. So I'm assuming I will speak something different and not bore you. So the idea of these workshops is to get our teachers more enough expertise so that they can confidently handle the astronomy content in schools. What we realized after talking to many teachers in many states is there are always common science teachers for all sciences, and so many of the school teachers, they come from different backgrounds. They have not necessarily studied astronomy when they were students, or they are not amateur astronomers. And as such, when they see some astronomy content, and students are always curious about astronomy, they will ask a lot of questions to teachers, and then teachers don't feel confident enough to answer those queries because they have never studied astronomy themselves. So that is why the teacher training programs organized by OAE is an effort to impart that expertise to as many teachers as possible. And in next 3 days, you will learn about many day-to-day phenomena where astronomy is involved, and there will be a lot of hands-on activities through which you can know about this how astronomy matters in your daily lives. I'm not talking about the claimed interference of astronomy, like some people say confuse astronomy with astrology. I'm not talking about that, but a lot of things around you, the calendars, the cycle of tides, everywhere there's astronomy involved. And in next 3 days, the resource persons will talk about these issues, and hopefully when you go back to your schools, you can convey this information not just to your students but also to your fellow teachers, and we will have multiplier effect by teacher empowerment. Thank you.
Thank you, Vijay. And just before we disperse on it, I would like to, if any of the teachers, we have a few good persons here. Of course, they will be also there in the last day. But if you want to ask anything, any queries, you can directly ask. Okay. Just introduce yourself.
Hello, I am Rajpal. I am a research scholar and I also collaborate with one of the company related to science communication. So my question is that, like in the discussion it was told that there is very less related to astronomy which is included in the syllabus, whether it's schools or colleges. So last 2 years I was working as a physics faculty. So the thing is that on a system level or the curriculum level, it should be the astronomy should be the decision regarding integrating astronomy should be more done by the curricular people, right? Apart from like what teachers do. So like how can we bridge that issue or how can we do that, make change in the system level or on the curriculum level? How it is possible? As usually as teachers, we have very limited time. So this is something that happens everywhere. In my past teaching experience also, it was the same thing. So how can we bypass this or manage this particular issue in the curriculum level?
Should I take this, Aniket?
Yeah.
Yeah. So, I mean, we are of course not expecting necessarily that the teachers will be able to influence the curriculum directly. But what we are trying to do is we are trying to conduct research in astronomy education, which may help to try to influence the decisions of what exactly are the things that get into curricula. Oftentimes, the problem is that when curricula are designed, you will see that people would like to put in astronomy, but given the kind of the knowledge of astronomy within the teaching community, etc., that is considered maybe that could be a hindrance in order to put in some of these advanced topics. But what our aim is to empower you guys to be able to teach these astronomy topics in an interesting way. Plus, in addition, to showcase that astronomy is like a magnet with which you can attract students into science education, and use astronomy as a topic to learn about not only science but the methodology of how science is done. So, with that kind of aspects, we may be able to convince them the various boards in order to integrate astronomy into the curricula. Astronomy may not be used as a separate subject in itself, but bits and parts from astronomy will be there in different subjects, say geography or sciences, and then that can then help to put or help to get students interested in these topics. I hope that answers your question. Maybe Aniket can add a few lines, or Neeraj.
Yeah. Yes. Aniket, do you want to say something?
Yeah, I will just add that, as Surut said, right, purpose of this workshop is not enacting a change in curriculum or syllabus, but given that whatever content is there, small level, at school level, we should prepare our teachers better to handle that content is first part. And second thing, even if there is not much content in the syllabus, there will be always queries from enthusiastic students because they are naturally curious about astronomy. So we prepare teachers to handle those queries. That is the purpose of this workshop.
Yeah, thank you. Neeraj, do you want to say something?
Yeah, I think most of the points have been covered already. I think there is like one point that astronomy has always been, whenever it is in the curriculum, has been seen as something which you add on and doesn't really gel with whatever is there, right? In the physics syllabus or all the standards, we have electricity and magnetism or mechanics, so everything, optics, everything is considered as part of physics, and the interrelation between them is brought out. Astronomy is always added on from outside, so it looks very, very strange and it's taught as if it's something completely different. And I think one of the things this kind of workshops will do is to kind of convince you that astronomy is indeed a part of physics, And it doesn't have to be a separate chapter, but it can be integrated into every single chapter of this. I think that is something I would want to stress on.
Okay, thank you. So I think with this we can conclude the inaugural address, and we will break for some 15 minutes. So we will start at 11:15. Is it okay?
That's fine with me. Yeah, you're giving me much more time to talk than I needed, so I will. I'm happy to have half an hour less and get you all to early lunches. Yeah.
Yeah. And again, we will all, I think, if everybody is free, we will meet on the last day, last session, and we will wind up by seeing what are the outcomes, best outcomes which can come out. And we are expecting a lot from this workshop because curriculum is one thing, but I think nowadays people are, a lot of things are getting, I was reading in one of my Facebook posts that people know more about, in general they know more about galaxies and black holes than they know about other human activities in other domains of knowledge. So astronomy is becoming popular and curious minds, young minds, they have a lot of queries and they go on asking. The best way as a teacher, actually we should quench their curiosity, we should say it in a better way. So this is the purpose of this thing. And there are a lot of talks, physical book, it is not that all are in the online, few persons could not make it. Or actually Neeraj was supposed to be the person who is coordinating this workshop. So he is supposed to be here physically for all the 4 days, but unfortunately he is developing in Mysore. There is a program, parallel program going on, so he could not come here. Aniket also is always busy with his Olympiad program. She is the chairman of National Olympiad, Astronomy Olympiad in India. And maybe sometimes we can arrange one Olympiad camp in Connecticut. Aniket, you can think about that. We can do it here sometime for our teachers. And so with that, I think we conclude and I thank all
I just want to say that I'm not the organizer. Giant is being very self-effacing. Giant is the main mover and driver behind all of this. So yes, please. Thank you.
Yeah. So thank you all. So we will meet again at, you can keep it mute and by 11:15, I will just, once more message that time you can again, maybe we can start.
It's the same Google Meet link, right?
He will be in the same link, same.
Yeah. I may also just
That's
keep
the
it.
only link which we are using on this.
Okay. Yeah. Thanks.
Okay, thank you. So we can go for the tea. Tea is arranged, so we can have it and come back. So we will, process should be the right interact. What he's saying is that it is not that all of you are just spectators seeing it. It is, it is both sides. We should ask questions. We want to debate. We should argue and fight and learn.
And at the end of the day, it's the end of the session on the third day, everyone has to speak.
We have various directions. From this video, we can see we will go to planning, we will go to observation, we will go to modeling, hands-on activity. A lot of things are planned. All the best practices will try to bring in. So now I think we will go for it. So we will have a group for
Madam is coming. Madam
we can take one photograph now. Please come and stand. I think you can put your banner. I think some of you can actually talk about and that will come that astronomy poster can you look in the backside. ശരി എല്ലാവരും നിന്നോ ഇവിടെ ആരുണ്ടോ are you there?
Yes, yes, I am.
Okay, so we can start. I think we are ready.
Okay, just give me a second. Okay, do you see my slides on full screen?
Yeah. I think
It's not full screen?
yeah, it's full screen.
Can you just check if it is? No, it's full screen for my screen, right? Okay, fine. Okay. So welcome back, everybody. So I want to talk to you about big ideas in astronomy, and it doesn't get much bigger than Indian astronomy, of course. Jayant Ganguly has said that he had sent you, he's given you a booklet with the same title published by the International Astronomical Union, and I've taken a look at that. I've taken some from there, but then I added some more ideas which I thought would be more relevant, and I've chosen a set of 26 ideas, and I'm just going to go through them one by one. I will spend maybe 2 or 3 minutes on each because that is what time, that's the amount of time we will have. I'm not going to talk about physics much here. That will follow in the talks hereafter in the workshop. You can think of this session more as a storytelling session. Okay, there will be a lot of history, a lot of stories there. The physics part I will leave to later. Right, so why do we talk of big ideas in astronomy at all? It's because astronomy, of course, concerns itself with the biggest and the largest and the most distant things we can think of. And not only that, more importantly, ideas from astronomy have influenced our perspective of our life around us and physics in general. And physics, of course, in turn influenced big revolutions in astronomy. But the many revolutions in physics which came from astronomy, including heliocentric theory or the theory of gravity, cosmology, and so on, and therefore that when you talk of big ideas in astronomy, there is a lot of history behind that. It's a very loaded term. So the first one, I'm going chronologically in this talk, starting from, let's say, 2,500 years ago. I think the first big idea was that the planets could be, they moved in supposedly strange ways, but at some point people realized, and roughly simultaneously in many different cultures around the world, including India, China, the Middle East, Greeks, and even in Mesoamerica and so on, that these planets, which they did not know what the planets were, but they were objects which seemed to move in the sky with respect to stars, you could predict their motion. And this was also true for the moon and the sun. And the fact that the sky is not something you blindly pour towards, but then you can actually understand and predict it, I think is the first big idea in astronomy in that sense. And of course, the orbits of the moon and sun were much more easier to predict, but then the orbits of planets are much more difficult, and that is why, for example, in the Ptolemaic model, as you see on the right side, they had to invent epicyclic theories. The famous English phrase "wheels within wheels" comes from this, where in order to account for the fact that we put the Earth at the center of the universe, and therefore the motion of planets, I think the Sassian from the Earth's reference frame is a bit strange. They had to put in epicycles where they said, okay, there is a mean deferent which goes in a circle around the Earth, but the planet goes in a circle around that point, and therefore it makes this epicycle that you can see in the bottom, right? And they had to, and as they got better and better observations, they had to keep refining and adding more and more epicycles. Till of course it fantastically blew up and then we went to the heliocentric theory. But the fact that we could even predict the motion of some planets on the sky which we could not touch or understand was the first big idea in my opinion. The second big idea was, of course, this about the fact that the Earth is a sphere and rotates about its axis. Now, you might think this is trivial, but it's not. If you did not learn from your school physics or geography, if you just go by what you experience around you, there is no reason to believe that the Earth rotates, right? You would believe that the entire sky rotates around you. There's nothing which tells you the Earth rotates because you know how it is to rotate. When you rotate or when you move around, the wind blows past your hair. Things, you can see things moving. You don't do that. You don't feel the rotation in your daily life, and therefore there's no reason to believe it rotates. And equally long back, say 2000 years ago, people did not travel that far. Maybe they traveled around 1,000 kilometers, and therefore it was not clear what the shape of the Earth was. In fact, it took Magellan to even go around the Earth once, right? And therefore there was no understanding of what the shape of the Earth was directly, experientially, and therefore they could piece things together from various bits and pieces. And therefore, at some point, different cultures at different times had to arrive at the conclusion through logical deduction and observation that the Earth actually is roughly a sphere. It's not flat, for example. And more importantly, that it rotates around its own axis every 24 hours, and it's not that the sky rotates around us, but the other way around. And for example, this was first documented record of somebody saying so, Aristarchus in Greece in a few hundred centuries BC. In the Indian context, this was clearly stated for the first time by Aryabhatta in Aryabhatiya and Golpada in around 6th century CE. And in fact, Aryabhatta says very clearly that he says, look, just like when you're moving in a boat in the river, you think the opposite bank is moving opposite to you, but then actually you're the one who's moving. Just like that, the Earth, the stars seem rotate around you, but it's you who are moving. And of course, it wasn't immediately accepted. A lot of Indian astronomers following Aryabhatta did not agree with it, but later, of course, people started going down to it. The fact that the Earth is a sphere, also the initial evidence given by cultures from India to Greece to China, etc., was also the fact that during lunar eclipse, the shadow of the Earth was always circle. But I'll come to that in a bit. This photograph itself is what is called a star trail photograph or long exposure photograph. You point the camera to near the North Pole, and then you let the camera record continuously for 2 or 3 hours, and you see this pattern. And you see this pattern because the Earth's axis of rotation cuts the celestial sphere in 2 points, the north celestial sphere and south celestial sphere. And because the Earth rotates around its axis from west to east, the entire sky seems to rotate around the same axis from east to west. And which means that, and since the Earth's axis points towards this supposed pole star, which is the center of these concentric circles, all the stars will appear to rotate around this circle, around this point in concentric circles. And you do not see it in your night because you see the stars at any given time. But if you take a long enough exposure, you can actually see the Earth. So this is basically telling you the Earth is rotating around an axis, right? And it tells you where the axis of rotation is meeting the sky in some sense, right? So this picture is tells you that the Earth is rotating in some sense, or at least one of it is rotating. And the fact that the Earth is a sphere is also something Aryabhatta said, is also something many Greek astronomers had said, and that is something which we now take for granted, but then it's something which was arrived at through deduction and a lot of argument with other astronomers at that time. The third idea I want to talk about is related to what I said before, which is that eclipses are actually caused by the geometry of shadows. And secondly, that can be predicted. This again was a very, very big thing. As you know, in many cultures, eclipses are seen as something harmful and to be feared. And I think we can all understand why, because you're used to you don't really look at the sky in your daily life. You just go about your work. You know the sun rises in the morning, sets in the evening. You know that the moon does its own phases of the moon thing. You use the moon and the sun for calendar. You know the stars are there somewhere. You don't really look up to the stars every day. But suddenly something happens where the sun disappears, right? And sometimes the moon disappears. And the sun disappearing in the middle of the day can, of course, it can be socially traumatic because it's something you do not understand. It can be scary, and therefore many cultures learn to fear it, and they have various theories about how it is caused and so on. And it's only later that people realize that this was caused by the shadow of the Earth, Sun, and Moon. It is not due to anything else. And this was realized by various cultures again in various times. Aryabhatta was the first person to say it directly and explicitly in the Indian context, of course. And the photograph you see is a total solar eclipse where the totality, you can see the corona, and now we understand what this is about. It was not also completely clear even in Indian context for a long time. A lot of astronomers argued with Aryabhatta saying, no, it is Rahu and Ketu are actually real things and it's not a shadow. For many centuries, he was laughed at by people like, Brahmagupta and so on. It was Lalla who came up in Gujarat in the 1100 CE who then argued that Aryabhatta was right, and then later accepted Indian context. And the fact that you could predict eclipses again was a very, very big thing, because not only was a strange phenomenon something you do not expect, but you could actually predict it. And of course, Aryabhatta gave the first formula for prediction, algorithm for prediction. The Babylonians had a much more formulaic way of predicting them based on patterns called the Saros cycle. The Greeks, of course, then started having more algorithmic ways of predicting it. And later, of course, now we know what to do. The fourth big idea is that the moon and planets shine by reflected light and not by their own. And this is something again which was a very big thing to arrive at, because it's obvious sun is the brightest object in the sky, and for many, I think till some 1800s it wasn't clear. Late 1800s people did not know how the sun got its energy from, let alone how the stars got the energy from. But then, when you look at the moon, it's clear that the moon shines, the planets shine, etc. But then you have to look at the moon carefully and look at the phases of the moon carefully, and then you understand that it's the moon and planets shine because they reflect light from the sun. And one evidence for it, of course, is the phase of the moon, right? Because the moon exhibits phases, the moon goes around the Earth. If the moon went around the sun, that would be very different. And Galileo, in fact, used the same principle, what you see in the bottom, right? Galileo, when he trained his telescope towards Venus, he saw Venus showed phases, okay? And because Venus showed phases, that was one of his evidence, very strong evidence that Venus went around the sun and not around the Earth, okay? The way it showed phases. And therefore, the fact that moon and planets aren't bodies by themselves as equally important as the sun, but they were subsidiary to the sun. And the sun has special importance because sun is the one which actually gives out all the light, which you then see planets and moon due to reflection, was a big idea by itself. Okay. I'll stop. I think every 5-6 ideas I'll stop and I'll take questions. Then the fifth, again, to get the number wrong, fifth idea is the axis of rotation of the Earth. Now this has been a source of controversy for centuries, okay, around the world, including India. Now we know that the Earth's axis, Earth rotation axis, points towards what we call the pole star or Dhruva Nakshatra. But that is just happenstance. It's not that somebody dragged the star and put it there, right? The star just happens to be coincidentally at the place where the Earth's axis cuts the celestial sphere in the northern hemisphere. But then, and the people made star charts, and people also then looked at where the sun was every month, every day of the year, and so on. And they soon realized, especially initially by the Greeks and the Romans and so on, that this was not probably totally true. The fact that the axis of rotation was very fixed in origin and it pointed towards just one place for a long time was not true. But it was true. But then they found evidence that the axis of rotation was precessing like a top. Right? And it was pointing, so the axis of rotation, we all know, it's inclined at 23.5 degrees from the perpendicular to the Earth's orbit around the sun. If you look at, if this is the sun, if this is a plane of the solar system, the sun is in the center, the Earth goes around this plane, right? And then you draw perpendicular, that is the axis of revolution of the Earth around the sun. And then if you look at the axis of rotation of the Earth around itself, that makes an angle of 23.5. And as the Earth goes around the sun, the axis stays the same direction, of course, right, like this. But then once every 26,000 years, it actually makes one complete revolution, describing a cone whose radius is, of course, 23.5 degrees. Now this astronomers found out over centuries because their tables went slowly wrong, right? The sun's position was slowly different, the tables of when something would occur would change, and therefore slowly over centuries people realized there must be something weird going on, and they realized that this was because the assumed axis of rotation was moving in so many words, right? And in fact, if you look at the figure, the main figure here, today, if you look at the bottom, it says today, and then that's where Polaris is, Dhruva, which is the last star of Ursa Minor, and the axis of rotation points towards Polaris today. But if you go to the left side, 3000 BC, it pointed towards a star called Thuban in Draco, right? And if you look at 14,000 AD, it pointed near the star Vega, which is very, very far off, right? And so on. And so this takes around 26,000 years to make one single circle. Now, the point is that we do not, because it takes such a long time, we need observations over centuries to make out this difference. Okay. So, for example, during Vara in Europe, at least in major in Europe, they slowly started realizing this was an issue, and they started incorporating corrections. Some schools did, some did not do. In India too, it was a huge controversy. For example, Varaha Mira did not believe it, but then the observations which said that it was true, and therefore it was some time before the Indian astronomers, ancient Indian astronomers, realized that there had to be corrections applied to the tables every few centuries. Since then, there have been two kind of schools of thought. There's one school which uses astronomy calculations for astrology, which of course is not science at all, which refuses to take into account this precision corrections, and therefore the tables are wrong. Many astronomy traditions in India, in various parts of India, have had astronomers who every 100 years or every 50 years will give you the correction which needed to be applied to a table which was written 100 years ago to correct for precision. But the fact that these were complicated processes, this was not something as simple as Earth being itself and not changing at all, but something is happening with the Earth's axis, etc., was a big idea. And the fact that your tables needed to be correct constantly was a big idea because it implied that you need to keep observing. So you cannot just observe the sky in one day. Aryabhatta said something, you then follow it for next 2000 years. That is not what you can do. That you cannot do that, but you need to constantly observe the sky, calculate corrections, check your predictions with observations, and if it do not match, you need to have corrections. And these corrections are primarily due to precision. They call Ayanamsha corrections in the Indian tradition. And every culture had its own fight with precision and kind of try to figure out how to put it together. And I think that is the next big idea. Okay, I'll stop here and get questions before I go to the next five. Are there any questions at this stage? Jayant? Jayant, should I continue or should I wait for some questions? I can't hear anything from your side, so I don't know what to do. Hello? Should I continue? No, but are there any questions about these five things I said so far?
Yeah, did you call me?
No, I had finished 5 points. I wanted to see if there are any questions on these before I move on.
So, please interact. I said you know it's more of an interaction. So, you can ask questions.
Because I want to stop here because everything I told you so far is about the ancient world, right? So, before 1500s or 1400s. So then I want to kind of stop here and take questions. If you had any, if not, I'll move on.
Any questions? Astronomy.
So, my name is Vasil. I'm from Parag Training and
Yeah.
I have asked you a question that was there any chance that ancient people believed that Earth was flat?
Okay, so of course, a lot of people believe Earth is flat because that is what your experience tells you in your daily life, right? And that's why big ideas are big because they went against what was taught at that time, which is why they're big, right? So of course, most people did probably think the Earth was flat long back, but we do not have good historical evidence about whether it was prevalent motion. For example, Aryabhatta said that the Earth is a sphere, right? There's no record of people contradicting him, whereas there are records of people contradicting him about the fact that the Earth is the one who rotates around its axis, right? So one is what astronomers believe at that time and what the public believe. There is not too much evidence that the public. It wasn't seen as something which was very strange or weird. So probably people accepted it a bit more easily than accepted the spherical part more easily than the rotation part. Same way, even if you look at the Greeks or Babylonian era, at some point it became clear that when they made statements like this, it wasn't accompanied by statements which said no, but then we had to convince them, or the fact that somebody said you're wrong, etc. So I think people slowly started accepting the fact that it was a sphere. But then I think right now the whole flat Earth thing has become a big thing the last 40 years because there's a new conspiracy theory in the US that everybody believes in, and everything that happens in the US gets a lot of media publicity, and therefore this flat Earth conspiracy has become very big now. But then there's no definitive record. But looking at what history tells us, it looks like at some point people started accepting it as obvious at some level among the general public. But then Aryabhatta did specifically say that, which means there was a need to say that at that point. But following that, it wasn't really they didn't make a much of a fuss about it in the centuries after that.
Yeah, I think it's okay.
Yeah, shall I move on? Okay. So just to recapitulate, we looked at the ancient world, that we can predict motion of planets, that the Earth is a sphere, rotates around its axis, that eclipses are caused by geometry alone and can be predicted. The moon and planets shine by reflected light, and the axis rotation of the Earth precesses every 26,000 years. Now these were big ideas in the ancient world, and they led to the phenomenal growth of astronomy in every culture, including in India. Now we move to 15th century plus. Okay. Of course, one of the biggest revolutions which we still know about and talk about and learn in school is the heliocentric theory by Nicholas Copernicus. Right. So till then, the prevailing theory in every culture across the world was that all the planets and the sun and the moon revolved around the Earth. Right. And this was because it was the obvious thing to imagine, because we are everything appears to revolve around us. That's one. And number two, of course, we're very important people. We're very important, and therefore everything has to rotate around us as well, right? So both beliefs kind of led towards the geocentric model. But then, if you remember the last slide before, the fact that you had to use a geocentric model and you had better and better data about planets implied that you had to build more and more epicycles to account for the observations, right? Because you're moving from the sun center to the center, and therefore you essentially have incorporated more and more Fourier terms if you know Fourier analysis, and therefore as observations became better, they had to incorporate more and more epicycles, so it became very, very unwieldy at some point. And then Nicholas Copernicus realized, sorry, somebody has to, yeah. So then Copernicus realized that if you put the sun at the center instead, and then you looked at the observations of that time, then everything became suddenly very simple. There was no need for so many epicycles, and things became drastically simpler. Now, there's a general rule in science which has evolved over centuries that if a simpler explanation, a simpler theory explains everything an earlier complicated theory did, then the simpler theory is probably true, right? And of course, later there was more and more evidence for heliocentric theory, especially by Galileo, which was persecuted by the then Catholic Church and so on and so forth, right? Now, but in the middle, and this was the biggest revolution in both scientifically and psychologically. Right? Scientifically, because for 2,500 years, people believed that the Earth was the center of the universe, and all the planets, sun, moon, stars, everything went around the Earth beautifully because, of course, Earth is very important, right? And then the scientific revolution was that you put the sun at the center, everything moves around the sun, and then your orbits become simpler. You don't need so many epicycles, and everything becomes drastically simpler. And it makes sense because sun is the brightest object in the sky, and therefore is probably the most important object in some sense, and therefore it makes sense that they go around the sun. Psychologically, it was a really big thing because we were used for millennia to think that we are at the center, and therefore the Copernican revolution, which is what is called the Copernican revolution, is basically much more psychological, which is that it takes man or human being from the center and puts us outside the center. Right, and this is and if you remember, there was this, there's a famous scene in Sherlock Holmes by Arthur Conan Doyle where Watson says, "Hey, Holmes, did you hear about the fact that people have discovered that is the Earth which goes on the sun and not the other way around?" And then Holmes says, "Oh, I would try to forget such a useless fact because it will cloud my brain with something else." Right? It's not. It's a very useful fact, no, because it's also psychologically a huge shift in thinking. It's a huge paradigm shift. In thinking, and that's called the Copernican revolution. I'll come to that the very last slide. The figure at the bottom center shows you something in between the geocentric and heliocentric, and I want to mention that. So before Copernicus brought up the heliocentric model, Tycho Brahe had come up with what is the Tycho Brahe model, where he said that all the planets go around the sun, but the sun then goes around the Earth, and this made calculations a lot easier than the geocentric model. And I bring this up because, of course, revolutions don't happen instantaneously. Even revolutions have steps to take, and it's a lot of work of a lot of people coming together where you suddenly make one leap. But then it's also interesting in the Indian context because Nilakanta Somayaji, who belonged to the very famous Kerala School of Mathematics, and you're sitting in Calicut right now. And the Kerala School of Mathematics is not that far from Calicut, which started by Madhava in the 14th century, the 1400s. He came up with the similar Tycho Brahe's model a few decades before Tycho Brahe did, right? And that's in a book called Tantra Sangraha, which is now published. As of 25 years ago, it's been unearthed and analyzed extensively, and therefore he had arrived at the same Tycho Brahe model where all the planets go around the sun, but the sun goes around the Earth. Okay? He did not make the leap into heliocentric, but that's an interesting work of history. So this is universally acknowledged as one of the biggest revolutions, the heliocentric or the Copernican revolution. Following that, so of course all of this was based on painstakingly taken data without telescopes, right? And basically using various observations of Mars and Moon and so on, and Mars and Venus and Jupiter and Saturn and so on and so forth. Then, of course, a few decades later came Isaac Newton. And Isaac Newton, of course, brought in the next biggest revolution, which is the theory of gravity. And it's not just a revolution because he said, oh, J1 by R squared, which is not a big thing by itself, but he was able to relate. He said, look, the reason if you throw a stone and it comes back to Earth, and that the cause of that phenomenon is the same cause which makes the moon go around the Earth, right? And that was the big leap, one of the big leaps, right? Which is why it's called a universal law of gravity. So it's universal. It applies to stones. It applies to apples falling from trees. It also applies to the moon. It applies to the sun. It applies to all the planets. It's universal, and that of course changed everything as we know it, as I don't have to tell you about. And then based on Newton's theory, you could then Newton understood why the planets move the way they do. Remember, before Newton, there was Kepler, and Kepler had used Tycho Brahe's observations of Mars extensively to come up with the Kepler's 3 laws of motion, right? That the planets go in elliptical orbits and so on and so forth, right? You know all the Kepler's and you know the Kepler's 3 laws. But those were based on observations, and he could not really explain why it was so. But Newton's theory, you apply Newton's theory and this pops up, all Kepler's 3 laws pop up. You could explain the motion. So you started going, so you moved from kinematics, which is just how things move in terms of velocity acceleration, to dynamics, which is basically involves you predicting how things will move because you know why they move, which is gravity, right? You use Newton's force law, and Newton's theory of gravity, and then you can predict how things move. And that was again a big revolution. On the right side is a screenshot taken from Newton's Principia Mathematica, where he talks about some aspects of elliptical motion. By the way, his Principia Mathematica is all completely geometry. All the proofs we do of Newton's theories These days with algebra, he did purely with geometry, so it's a very difficult thing to read. In the center, you see, of course, a illustration of how the moon or any planet goes around the sun due to gravity, balancing the two forces, centrifugal force and the gravitational force. And on the left side, of course, you see this. But the main picture is Halley's comet, and I want to stress that because one of the biggest applications of Newton's theory immediately was the fact that Edmund Halley, who incidentally was one who convinced Newton to publish his theory at all, he looked at various comet records over the decades or centuries, right? And comets again were feared by many people, just like people feared eclipses because they did not know what they were, and they kept coming randomly. You don't know when they came. They came whenever they wanted to, went away whenever they wanted to. But then he then looked at the orbits of certain big comets, and then he said, look, I think there's the same comet coming back again and again. And based on earlier observations of the comet, he then used Newton's theory to predict when this particular comet would come again, and it did after he died, right? And that was seen as one of the first major proofs of Newton's theory, which is why I put Halley's comet in the diagram. Now, Newton's theory then gave you dynamics, and then with dynamics, of course, you can measure the universe, you can do everything you wanted, and slowly using Newton's laws and observations, for example, of transit of Venus, which is what this figure on the top right shows you, people started getting an idea of the distances within the solar system. And they realized very quickly that these distances were not like 10,000s of kilometers, which was earlier thought. So various cultures across the world earlier, before 1400, had estimated distances and sizes of objects, and they of course came up with numbers like 100,000 kilometers, 10,000 kilometers, etc., etc. They're completely off the mark. Using Newton's laws, you could then start measuring the sizes and scales within the solar system. So that was the known universe, and they realized very quickly that the scale was immense, right? And the fact that these scales were immense was a big realization, and that's something again which takes you beyond yourself from the distances you're used to on Earth to something which is unimaginable, right? What you see in the center figure are all the planets arranged in logarithmic scale of distance, right? So the fact that they're kind of equally spaced, you can see all of them, is because they're logarithmically spaced. The bottom left figure has them in linear scale, and you can linear scale, you can tell really exactly how close, how vast the universe is, how the solar system is, because the first Mercury, Venus, Earth, Mars are seen in the first four dots, right, on the extreme left, and then compared to that, you can see how far Neptune or Pluto is, right, and therefore, and how did they get to know this beyond a point? Beyond a point, so this is due to. They could measure the distance within the solar system by observing transit of Venus or Mercury, etc., from two different vantage points on the Earth, and then triangulating. Triangulation is one way of saying parallax, right? And then later, they then used the same parallax in the 1700s and early 1800s, late 1700s, early 1800s. They applied the same method of parallax to stars, and they found that some stars showed the same parallax if you look at its position every 6 months, because the sun is here, the Earth goes around the sun's orbit every 6 months, and therefore, just like in normal parallax, when we tell your students put your finger out and look at the finger against backward objects, the baseline is the distance between the two eyes. Same way, if you take the largest baseline you can achieve on Earth is, of course, 12,000 kilometers, but then if you take the Earth's orbit itself from, let's say, January to July, that gives you basically a 2 astronomical unit diameter baseline. With that baseline, you can start measuring parallax on nearby stars, and then they found, which is what the bottom right figure is about, and then they could measure the distance nearby stars, which is even more immense, right? So if you again look at the logarithmic scale in the center, the nearby star Alpha Centauri is marked, but then if you want to mark that on linear scale, you have to go to like a few kilometers from where I'm sitting. Okay, so that was the next big leap. Now the ninth thing which I am always amazed by is the discovery of Neptune, and this is something I think many people don't really emphasize, but I think it's a beautiful story. Again, again based on Newton's laws and really good observations. Now, Uranus was discovered very quickly after the telescope was invented, a few decades after that, I think 100 years after that by Herschel, right, as the next planet after Saturn. Now, then they observed Uranus's path for over 100 years, almost like 50, 60 years, 70 years, right? And then they applied, now they have a theory to predict how the orbits will behave, Newton's laws. They applied Newton's law of gravity to the observed orbits of Mercury, Venus, Mars, Jupiter, Saturn, and they all behaved perfectly. You could explain the orbits of all of these planets perfectly with Newton's laws. Therefore, Newton's laws were great. But when it comes to Uranus, there were some differences between the predictions of from Newton's gravity and observations. And of course, this is happening around 1840s, 1830s. People were realizing that there was a difference, and therefore it became a big problem. Now, when Newton's law is wrong, people consider that Newton's laws are wrong, right? So some groups said no, maybe Newton's law is correct, but then they're not accounting for all the gravitational forces in the universe. Universe at that time, remember, is a solar system, and therefore maybe there's an extra planet beyond Uranus whose gravitational field is affecting Uranus' orbit, and that is why there's a discrepancy between observations and predictions. Now, this is a very bold claim to make. It's also a very bold claim to make that Newton's gravity theory was wrong. Both are very bold claims, right? So the two groups, one in France, one in UK, one in England, who then tried to use the observed path of Uranus and the prediction to then estimate where the supposed new planet should be, so that its perturbations on Uranus will explain the discrepancy. Okay, so Leverrier, so Adams and Leverrier, Adams in England, Leverrier in France, then predicted where this would be observed, and Leverrier's observations were then taken up in the Paris Observatory by someone who then discovered a planet very close to the prediction, right? And then later it's also independently discovered later in the UK. This was a huge, and the reason I'm stressing this discovery of Neptune is that this is in some sense the first dark matter we have, right? So we knew you saw planets move, you saw their orbits. You did not agree with what your theory had predicted, and therefore you could then have disbelief about a theory. But then a very clever explanation is that maybe the theory is telling you that you believe your theory, and the theory is telling you there's some other object who you do not know, you never seen before, you do not know anything of, you never heard of, which if it existed, I'm sorry, I think somebody needs to mute. Yeah. And if it existed, I can calculate from my theory where it should be, and I'll go look for it, and then I find it. That was brilliant. It made the news in all the newspapers around the world at that time. And the fact that you could discover a new planet based on its unseen influence on what is on another planet was revolutionary. This again was a very big thing. Okay. Now I'm going to move on to the sun. So the last four, are there any questions? To recapitulate: the heliocentric theory, the Newton's theory of gravity and dynamics of objects, distance to the solar system and nearby stars, and finally discovering Neptune. Are there any questions about this?
Any questions?
So Neeraj, just a small point that the Neptune, I think, was discovered not in Paris Observatory, but this in Berlin Observatory. So people from France did not take Leverrier seriously, it seems.
Yeah. There was a lot of those. There was huge. Correct.
Yeah,
Correct. But the prediction was made from Paris Observatory.
Yeah.
And then Leverrier got the credit, and then the British and the French had a huge fight.
Huge fight. Yes.
For years and years about who should get credit for it. Yeah. So, are there other questions about these four things before we kind of move on to the sun and beyond?
So in the geocentric model, it was successful in some aspect, right? Even though like what you are saying regarding the heliocentric theory, like there is a philosophy called as Occam's razor, where like the simpler explanation
Yes.
is preferred over the complex explanation. But with the very restricted equipment they had, what was the modeling that they did to find something fascinating as geocentric model, even though heliocentric model was later accepted by the
Okay.
process.
I think I understand your question. So the geocentric model came up because that is the obvious thing to do, right? I mean, if you were living if you did not know any physics or ever heard about any of this, you look out and you observe the sky every day, you would obviously assume that everything went around the Earth, but that's what you see. It's the obvious thing to assume, right? The geocentric model. And therefore, then you could be happy with that. But then astronomers 2000 years ago said, okay, I want to know, predict the orbits of these planets, see if the planets' orbits had any pattern to it, right? So I know that Saturn goes once around me with respect to stars in so many years, but can I then predict where it will be next year or 3 months from now, or how where Mars will be 3 or 4 years, 4 months from now, etc. When you start doing that, then you have to you build a model by which you can predict its path, right? So then that model assumes geocentricity, which means that, and the easiest explanation is they all go around Earth in a circle. So people tried that long time, right? Everything goes around a circle. That works really well for Sun and the Moon, of course, but it doesn't work well for the planets because as you know, the planets go around the Sun, right? So if the Earth goes around the Sun, then you can say, okay, Sun goes around the Earth. As far as calculations go, doesn't make a difference. If the moon goes on the Earth or Earth goes on the moon, calculation wise doesn't make a difference. But then if the planets go around the Sun, and then you tell them and you tell yourself that it goes on the Earth, then assume a circular motion or a circular orbit for planets will not obviously work. Now, therefore, but deviations from the circle will be more and more as you get better and better observations with more and more accuracy, right? So, for example, Mars, for example, in Indian tradition, it's called Vakram, right? So, Mars is going on Vakram, right? Or Saturn is going on Vakram, or something, right? Basically, Vakram is retrograde motion. So, you look at Mars, it will be going around the sky. At some point, it will turn backwards. Okay, so it will go on the sky. It will turn backwards for some few weeks, and then it will continue to go along this path again. Right? Now, why on earth would anything do that? Right? I mean, why on earth is a bad phrase, but why would any planet do that? Right? It seems very, very strange that a planet will go backwards and go again, right? But even if you ignore the retrograde motion, it was clear that if you assume a circular orbit and keep predicting the planet's positions farther and farther away in time, your errors are accumulating much more. So then, for example, Ptolemy in Greece came up with the epicyclic theory, where he said, okay, there is a fictitious point going around the Earth in a circle, but the planet goes around this fictitious point in a circle, and therefore it is carried around the Earth by this point. Therefore, it kind of does this looping motion, right? And that seemed to account for a lot of observations really well, including the backward retrograde or Vakra motion. But as you then got better and better observations of, let's say, Mars, especially because you had more accurate readings based on your Shanku, Nomo, or your large instrument, masonry instruments, and so on. It was clear that was not sufficient. The predictions and observations were not agreeing. Then they started having, okay, it goes around this point going around the circular orbit on the Earth is called deferent. The planet is deferent. Okay. And there's the corresponding term in Indian astronomy. Now the planet goes around this deferent and therefore goes in cycles around the Earth. Then they said, okay, no, this is not enough to explain prediction. Therefore, the planet now goes around another point, which then goes around the deferent, which then goes around the Earth. And then you got more observations again, but then your predictions then diverge from observations farther away in time. Then they said, okay, we'll add one more circle, within one more circle, within one more circle, within one more circle, and so on. This is what the whole phrase wheels within wheels came, right? And then it became more and more complicated to explain observation. At some point, it becomes very unwieldy and also difficult to believe that any universe, if you look at the bottom right, this is one of the epicyclic theories model at some point, right, in the 1300s or something. Very difficult to believe any planet will do something this silly. But then you had no idea as to why or why not. And then you move to a heliocentric model, then all of these disappear, all these epicycles. Okay. So that was the big thing. But then it's not as if geocentric model is but then you could always, but there's a point, right? So it's wrong in principle. But then as far as calculations go, you can keep getting very accurate values with a geocentric model if you just keep adding more and more epicycles, right? If you know a bit of advanced maths, every cycle you add within one more cycle, you're adding one more Fourier term of expansion to convert from heliocentric to geocentric, right? And therefore, if you keep adding more and more cycle within cycle within cycle within cycle for each planet, your accuracy of calculation will keep improving and improving more and more. And therefore, you can just do that forever, except that it's going to be at some point very painful. That is the point. Any other question? Or shall we move ahead?
Sorry, Niraj, can I add one more small thing?
Yeah,
Yes?
please.
Yeah, so
Yeah.
I mean, in addition to exactly all the things that Neeraj raised, there is also an observational reason which could not be explained at all in heliocentric theory. And that was the fact that if you look at Venus and if you observe it through a telescope, then just like Moon shows phases, the planet Venus also shows phases.
Yeah.
And this becomes
Yeah.
impossible to explain in a
Exactly.
geocentric
So that is at the bottom right. That's the bottom right. Yeah. So Galileo had seen this, and one of Galileo's evidences for supporting Copernicus was the fact that Venus and Mercury show phases. But of course,
Yes.
Copernicus did not know about it. But
Yeah.
this is one of the main evidences Galileo had put forth, saying.
Yeah, exactly. So once you have observations, then it really helps you to distinguish between these things,
Exactly.
even if you apply these Occam's razor.
Exactly, exactly. But remember, Copernicus revolution is pre-telescope, so he
Yes,
came up with
yes,
this
of
pre-telescope.
course.
So that so
It is.
yeah, exactly. Okay, let's move on then. So the 10th idea I want to talk to you about is that the sun is a star. Now the sun is something which is there in our life a lot. It gives us light and energy and so on and so forth, heat, and it's worshipped as a god in many cultures because it's seen as all powerful. And then at night you have these stars which are points of light which you do not know anything about, and there's no reason to think that the sun is also a star, right? And therefore at some point it was a revelation, much before telescopes, of course. I don't really know who all proposes at what time. At some point there was three people hypothesized the sun also is a star, but the stars are like the sun but very, very, very far away. And that idea kept circulating in various cultures over centuries, of course, till with modern physics, then one could then kind of show that was indeed true. Now, the fact that the stars are like our sun, or sun is just like any other star, was a big idea, of course, right? Which is not easily imaginable from your daily experience. And the second part of the sun, which was realized after Galileo started looking at the telescope, the sun is dynamic. So the strip on the grey color strip I showed you are actual hand drawings by Galileo himself every day, every successive day, and he found that there are these dark spots on the sun called sunspots. And as the day progressed, as every successive day, the sunspots seem to move across the face of the sun, which of course he used to very easily prove that the sun also rotates around its axis roughly every 1 month. But the fact that there were these blemishes on the sun's surface was also a very new idea, because the sun was assumed to be this pristine, pure thing, which was like a god, right, in some sense. And then the fact that the sun also had these features which moved, etc., showed that sun was basically like much more down to earth in some sense than like a pristine god in the sky. And the bottom picture shows you the number of sunspots and the latitude at which they occur on the sun as a function of time, starting from 1870 or 1875 to 2020. And you can tell clearly that there is a cycle which it's called 11-year solar cycle. And the fact that the sun is a dynamic object, things happen on the sun, they change over days, over weeks, over hours, over years, was a revelation. And what we now know about the sun based on all its dynamics is now we apply to other stars to understand them better. Okay, so that is the 10th big idea on top. Then the next big idea is, so all of this was basically based on observations of the sky with your eyes or with the telescopes or imaging, right? Basically images. Now we move on to what you would call the birth of astrophysics. Astronomy you could loosely define as a field which talks about what you can basically deduce by looking at images, looking at photographs, and measuring the positions and the motion of objects in the sky. None of this would tell you what actually the object was made of. I can predict exactly how Mars will move around me using Copernicus principle and the Newton's law of gravity. That will not tell me what is the temperature of Mars, what is the composition of Mars. I can tell you exactly how the sun will move. I can follow sunspots every day. That will not tell me why does the sun shine. I can calculate distance to nearby stars using parallax. That will not tell me why are the stars so faint, or how bright are they really, and how much mass is there, for example. All of that, which is physics. Physics is about measuring quantities and aspects about what something is made of, how does it function, etc. Astrophysics had to wait till the advent of spectroscopy. Okay, I won't go into too much detail. There's a whole talk by itself. But people started looking at spectra of sun and the stars, and they also started looking at spectra of gas which they heat up in the lab, And they very soon realized that when you look at the spectrum of the sun, for example, the background image is a spectrum of the sun just folded from red to blue in lines, so it will fit into a page, and you can see all these black lines. It's called Fraunhofer lines. These are absorption lines, and you might know already that you have an absorption spectral line or emission spectral line in an atom when an electron makes a jump from one energy level to the other energy level. Right? In an atom, electrons can't be wherever they want to at any energy. Let's take a hydrogen atom. The electron can only occupy discrete energy levels, which is what quantum mechanics later came and explained. And when an electron makes a jump from a higher energy level to a lower energy level, the energy difference is emitted as a photon or a particle of light. The photon will have energy corresponding to the energy difference and therefore a corresponding frequency, and therefore it will be seen as an emission line. If instead an electron jumps from a lower energy to a higher energy level by absorbing the same frequency light, then there will be an absorption, which is what you see in front of you. Okay. Now, people also could heat up gas in the lab. Let's say they heat up sodium gas or carbon or nitrogen or oxygen, and they could find each gas gave its own set of distinct spectral lines at set of frequencies unique to the element. It's like a fingerprint, chemical fingerprint. Therefore, if you give me a set of spectral lines from a particular element in the lab, I'll tell you which element that is because it's a unique fingerprint. Then people started putting these two together, spectra from stars and sun and spectra from the lab, and they realized that they could then match them. And the fact that there's a particular line here, this particular frequency from sodium in the lab, and you can measure the same absorption line at the same frequency in the sun, meant that now you knew that there was sodium in the sun. And the advent of more physics, including Megha-Saha's equation, ionization equation, you could then predict the temperature of the sun where this emission absorption was happening. You could also, from the relative strengths of the various spectral lines, tell me how much of each element there is on the sun. This is astrophysics. Now I can tell you, looking at the spectrum, the sun has these elements. It has carbon, nitrogen, oxygen, fluorine, neon, oxygen, etc. I can tell you at what temperature they are at. I can tell you how much carbon there is with respect to oxygen, how much carbon there is with respect to iron, and so on. Now I can tell you the chemical composition, the temperature, the pressure, and you can also weigh the stars in the sun. Now I'm in the realm of astrophysics, where I can tell you the physical and chemical properties of these objects, and therefore I can also start talking about how they shine, for example. Right? And the fact that the sun and the stars are made of the same atoms and elements as that on the earth was again a big revelation. It took around some 60-70 years to arrive at this conclusion. That happened during the 1800s, basically. Okay. Including, and one big part of this story is the discovery of, there's only one element that's been discovered outside the earth first before being discovered in the lab or around us. That element is helium. And a big part of the story of connecting what you see in the lab with what you see in the stars is the discovery of helium. It was discovered during a total solar eclipse on 18th August 1868 from Guntur and Machilipatnam in Andhra Pradesh during a total solar eclipse. That's a historical aside. Okay. So I told you that now, so we now know the temperature, pressure, size, luminosity, mass, etc. of stars, including the sun. But then but that doesn't tell you where it gets energy from, and that had to wait for a bit. Eddington, before quantum mechanics really came into its own, had hypothesized that the only source of energy which could give as much energy as the sun is radiating for as long as the sun has been radiating has to be when four protons join together form a helium nucleus, and that was proved right later. And this is done through what is called the proton-proton or PP chain. Okay, so the sun's center is extremely hot. It's a few million Kelvin. It's around 15 million Kelvin, and it's very hot because the gravity of the sun has compressed it to such a large extent that at the center is very, very hot. And at this temperature, you can have protons coming and fusing with each other. So there's no atoms or elements anymore. All atoms are completely ionized at the center because it's very, very hot. And therefore you have protons and electrons. You don't have hydrogen atoms. And the protons can come together in this. And one of the ways in which they come together is what is shown on the left. So you have two protons coming together to form deuterium and so on, and they combine to form helium-3, which then combine to form helium-4. And we all know E equal to mc squared. There's a mass difference between the 4 protons and the helium-4, and the difference of energy is given out, is emitted partly in photons and partly in neutrinos. Okay, and the energy in photons, which is emitted as gamma rays inside the center of the Earth, is what propagates outwards and comes to us as visible light, primarily visible light outside. So therefore, we now know the stars are nuclear reactors, nuclear energy. can the person be muted? Surendran Ponnagar, please mute yourself. Thank you. And therefore, we realized around I think 1920s or so that late 20s, late 1920s, that sun and the stars are powered by nuclear fusion, and if you combine protons and form helium, and then helium can probably combine and form heavier atoms and so on, heavier nuclei, like I showed you on this figure here. Helium can burn to form carbon, carbon can fuse to form oxygen, burn is the wrong word, sorry. Oxygen can fuse to form neon, magnesium, silicon, and ultimately iron. And therefore, people realize that all heavy elements are produced this way, can be produced this way in the center of stars, right? So it's a huge revelation that that not only are stars powered by nuclear fusion, and nuclear fusion is the only mechanism which can give the amount of energy we see for such a long time as we know stars and the sun exist, but it is also the factory for producing or creating heavier elements. Okay. Once we realize that, of course, then the famous statement by Carl Sagan and nowadays by Neil deGrasse Tyson that we all made of star stuff. And this, of course, is one of we all made of star stuff is something people talk about as in the same breath as the Copernican revolution. I think that's true. We all realize, and you look at what the stars produce. Stars heavier than the sun will produce heavier elements. Okay, the sun will not produce anything much more than carbon, nitrogen, oxygen, and so on before it ends as a white dwarf. But stars which are much more massive than the sun will then go on to produce heavier elements than even nitrogen, oxygen, and so on. And the more massive the star is, the more heavier the elements it will produce. Still iron, because binding energy of iron per nucleon is the largest. And the elements heavier than iron are produced when the star explodes. And in this process of explosion, iron then combines with excess neutrons to form further heavier elements. Now, and therefore, hydrogen and helium and some lithium we know was produced in the Big Bang. I'll talk about Big Bang later. Every other single atom, stable atom, which is heavier than hydrogen, helium, or lithium, was produced inside a star. Now, we are all made of carbon, nitrogen, oxygen, phosphorus, sodium, etc., which meant that every single, for example, carbon atom in our body, in your body, was created during nuclear fusion inside some star previously, right? And that is a very profound statement to make. And that is why, that's what Carl Sagan meant when he said we are all made of star stuff, literally made of star stuff, in the sense that every single atom in a body which is heavier than hydrogen was every single, the nucleus of the atom was literally made inside a star, or when a star exploded. And this is a periodic table which tells you the astrophysical or cosmological origin of every element. And hydrogen, helium, of course, is Big Bang, like I said. Blue is low mass stars. Low mass stars in this case includes the sun, and so on and so forth. So every single atom is made in this way. Okay, that's why Carl Sagan famously said, as the quote here says, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are all made of star stuff. Okay. Now, are there any questions about this aspect? Quickly, I'll take maybe one or two, then we go on next. We have 13 more to go. Okay, if not, let me continue. So then, now, as we get better and better tools of measuring distances and we get better and better telescopes, our view of what the universe contains keeps expanding, right? Long back, people thought that our solar system basically was the universe, right? If you look at writings or theories or even diagrams made before the 1400s, it will be the universe would be the solar system, and then the stars would be on a single layer surrounding it. Later, people found out with parallax that the nearby stars are actually quite far away, many light years away, which meant that the farther stars were even farther away, and therefore suddenly our notion of how big the universe was expanded. And then very soon people realized that we live inside a galaxy called the Milky Way, and we're not even in the center of the galaxy. Again, Copernicus principle, we're not the center of anywhere. We are always in the periphery of things, just by probability. And people start measuring the size of the galaxy. And they realized the size of the galaxy was again immense, right? If you look at the bottom right figure, our sun is 28,000 light years away from the center of the galaxy. The galaxy's thickness is around 1,000 light years, and the galaxy itself goes on to around 35,000 or so light years in radius outwards, which means the light from the galactic center which reaches us now, took 28,000 years to come to us, which is an enormous distance, right? And we also, along with doing this, we can also map out a galaxy. We figure out our galaxy's shape is basically like a flat dosa, and it's flat with a small bulge in the center. This is what the edge-on view at the bottom right shows you. And it's not just pure flat like a dosa, but it has these spiral arms where you see a lot of star formation happening. And we live very close to one spiral arm called the Orion Cygnus arm, which is seen in orange in the figure, called 2b. And you can see the red dot which says solar system, right? So we are very close to the Orion arm basically. And to not only to measure the size, to get to know the shape and also the components of the Milky Way was a big step forward. For example, we know now the Milky Way has stars. It has gas from which stars are born. It has gas which is ejected by the stars, especially when they die in gigantic explosion like supernovae. It has magnetic field, it has cosmic rays, and it has molecular gas, it has atomic gas, and all of this put together is our Milky Way galaxy. So that is the next level of expansion of our understanding of what the universe is about. Now I'm jumping back and forth in time. This is something which happened the last 10 years, and then I'll go back to the galaxy again. If you ask any astronomer some 10, 12 years ago how many planets are there in the galaxy outside the solar system, they might say maybe one or two. We only had evidence for one or two, 51 Pegasi and Epsilon Eridani, for many decades. And if you ask astronomers, do you think every star has a planet? The answer would be, I don't think so. There's no evidence for it. Maybe not. Okay. But then with the advent of new telescopes and precise engineering and therefore excellent observations in the last 10, 12 years, we now know that if almost every nearby star we look at, we find they have multiple planets, not just one. Okay, the blue thing on the top right is a actual photograph through a telescope where they blocked out the central star marked by the green cross, and they can actually see the three planets directly. Right, the bottom right, which is the ring, is again an actual photograph image taken through a sublunar telescope called ALMA, where the central star is very dim. You can see a ring around it. The ring is basically a ring of debris when this star system is forming, which will then become planets in the future. But you already see one planet which is just formed, which is just inside the ring on the top part. That's a planet that's already formed and cleared its orbit. The ring is going to form a giant planet at some point. Right? So now we can image other planets. But more importantly, if you look at the graph on the left side, the graph plots the radius of the planets which we discovered versus their orbital period. And you can see so many points. As of now, we have discovered more than 5,500 planets. And it looks like every star we look at will, especially the lower mass stars, have multiple planets on it. This is again a huge revolution in our thinking, our understanding, because we do not even know that we would ever be able to figure this out. Those planets will be very, very, very faint far away. But then we now know that not only do we know that every star has multiple planets, we also imaged a few planets directly. This then is important because then the obvious question then is that if there are so many stars in our galaxy, so many galaxies in the universe, and every star has a few planets, the number of planets in the universe is an unimaginable number, and therefore the probability that there is some form of life on planets is become almost one, if you ask me, right? So 15 years ago, if you ask astronomers, is there life on other outside the solar system, they'll be, I don't know, maybe not, who knows. Now, I think most astronomers will agree that it's extremely improbable that there's not some form of life somewhere in the galaxy, because now we know the literally trillions and trillions of planets just in our own galaxy, if not other galaxies, right? So the fact that all stars have planets has profound implications for the question of whether there is life outside our solar system at all, right? So that's the big thing. And related to that is the fact that for life to form, of course, you can't just put carbon and hydrogen and form life. You need complex molecules. Whatever form the life could take, you know that it has to have complex molecules. And we now know over the last 20, 30 years that the fairly complicated hydrocarbons or molecules with carbon atoms in them have been found in space in colder molecular clouds in our galaxy and also in other galaxies. The spectrum you see is just a small part of the spectrum in a submillimeter taken against a star-forming region or a molecular cloud in our own galaxy, and you can see the complexity of the molecular spectrum. And some of the molecules have been found in space in our own galaxy has been listed on the right in this vertical column. And you can see, the fairly complicated molecules, right? The last one is C60, the Buckminster-Fullerene molecule. And therefore, we know if there are so many trillions and trillions of planets, and we know that there are complicated hydrocarbons, or at least carbon-based organic molecules which are already found in space, then the probability of forming some kind of life is much higher. In fact, we even found amino acids. We found uracil in comets and asteroids, in comets, for example. Right? So we even know that very basic amino acids already in the solar system outside the Earth. And therefore, the discovery of exoplanets mixed with the discovery of molecules in space directly tell us the probability of life elsewhere is very high, much higher than we thought a few decades ago. Now let's again make a big leap outwards. We for till around 1910, 1912 or so, astronomers thought that the Milky Way galaxy is the only galaxy in the universe. And they did not, and they had all these tiny fuzzy blobs they could measure, they could make out in the telescopes. They were given names like NGC 4534, NGC 2522, etc. And these were fuzzy and they were thought to be gaseous nebulae in our own galaxy, okay, or maybe slightly outside. So people thought for a long time that the universe was made of just our galaxy. Then again, remember Copernicus, right? Copernicus tells you that if you think you're very special, you're almost always wrong, right? And therefore, there's a very famous debate called the Shapley-Curtis debate, based on observations, where then it was shown conclusively that a lot of these small fuzzy objects we thought were gaseous nebulae in our own galaxy were instead independent galaxies extremely far away. And therefore, now a Milky Way itself is no longer special, but just one among billions and billions and billions of galaxies. The image you see here is called the Hubble Deep Field. It's a part of a very deep exposure by the Hubble Space Telescope. Every single thing you see here is an extremely distant galaxy, each of which, many of whom, especially the bright ones, are much bigger than our own Milky Way galaxy. So the next big idea was that our Milky Way is no longer that special. Milky Way is one among billions of galaxies, not trillions of galaxies, and the universe is far bigger than we ever imagined because it has to hold all these galaxies within itself. Okay, I'll stop here and take questions, and then the next part is basically cosmology. Are there any questions till now?
Any questions? Yes, you have something.
See, because I started with Mars's orbit, and then I come to the entire universe made of galaxies. We have gone a very far distance in like 1 hour, right? So and this is what big ideas do to you. So I'm sure you're overwhelmed a bit. So I want to kind of pause for questions.
Anybody? I think his questions will come slowly because
Okay. Yeah, the first section, so everybody, I think, is a bit shy. I'll move on. Okay. So remember, we come a long way. Okay. Then the next big revolution was, of course, Hubble, based on work by Lemaitre, where he looked at the spectral lines from all these galaxies. So all these fuzzy objects, which was then conclusively shown to be other galaxies outside our Milky Way, very far away. Then people started worrying about how far they actually were, right? And at some point you could do that through various ways, by locating some very special kinds of stars in these galaxies and looking at how they vary in brightness, etc. I will not talk about that. But then at some point, Edwin Hubble, and other people started looking at Slipher, Lemaitre, etc. Started looking at spectral lines from these galaxies, for whom they already had the distance from some other method. And they found that the spectral lines were all redshifted. Now, I don't know if all of you know what redshift is or Doppler effect is. I won't explain that now. I'll ask Jayant Mangal to maybe explain that in a later session. But basically, the basic idea is that if something is moving away from you, if something is emitting light towards you and is moving away from you, that light will be shifted towards the red or lower frequency. As some body is emitting light and moving towards you, then the light will be shifted towards blue Earths or to a higher energy. And this is what you see also in the case of the sun. In sound, the famous example is, of course, your fire engine is blaring sound coming towards you, its frequency is higher, that is going away from you, the frequency is low. Same principle. And I'm not going to explain all that in detail, but basically Hubble discovered that a farther away a galaxy is, it's appearing to be moving away from us faster. And all galaxies are moving away from us, except for one or two examples of very nearby galaxies like Andromeda Galaxy. No galaxies seem to be coming towards us. They're all moving away from us. And the farther away they are, the faster they're moving away from us. This doesn't mean that they didn't discover that Earth is going to get coronavirus and therefore best to keep away from us and be in quarantine. Again, Copernican principle, if everything is moving away from us, that doesn't mean we're the center of the universe. It means that our perspective is wrong, right? And therefore very clearly, and Hubble realized that this also meant that if you're sitting in any other galaxy, it will seem that every other galaxy is moving away from you in that galaxy. And putting all this together, it was soon realized by many people that this was evidence that the entire universe is expanding in 3 dimensions, okay, from each other. And because the universe is expanding in 3 dimensions, each galaxy was moving away from each other, and the farther away a galaxy is, it appeared to be moving faster away from it. Now, therefore, the fact that the universe is expanding was a big discovery, and there's a huge history towards it. For example, Einstein's equations initially showed he understood from the equations the universe must be either expanding or contracting. He did not believe it, and therefore he fudged the equation by what is called a cosmological constant to make it static. Because at that time there was no evidence to indicate that the universe was doing anything but just be static. When Hubble's expansion was discovered, Einstein realized that he made a big mistake, and yet another discovery attributable to Einstein could have been that he discovered the universe was expanding, but he did not do that, unfortunately, because again, this was too big an idea for even Einstein. Right, and that's interesting to think about. And the fact that universe is expanding is something everybody knows in popular culture now. We know what Hubble's law is, but that time it was a huge revelation. Again, a very, very big idea. And if the universe is expanding, then at some point it must have been smaller at the beginning, which led to the next. Now, before I come to that, now I talked about Einstein and how Einstein's equations predicted even for him that the universe must have been expanding or contracting. And that was also a big revolution. And I'm claiming all of this into astronomy. I think I have a right to do that. Newton's law of gravity, I had said, was a big idea in astronomy. And because, of course, gravitating matter is in the domain of astronomy. Same as general theory of relativity, though it was arrived at for many reasons. It wasn't purely astronomy motivated by observations. It was motivated by other mathematical and other physics reasons. We are going to claim general theory also as a big idea in astronomy. I don't have to tell you about this. This is there in popular language everywhere around us. Einstein then modified Newtonian theory of gravity, made it much more accurate. He realized that things cannot act at a distance instantaneously. That you have to account for the fact that if the sun does something, then it's effectively felt at Earth only. At least at the speed of light, not instantaneous, and therefore then he came up with this modified theory where the space-time is considered as an entity which has a curvature due to bodies having mass, and as I think John Wheeler famously put it, massive bodies cause a curvature in space-time, and this curvature then causes other bodies to move around it. And instead of talking about gm by r square, you say, okay, I will now look at a geometrical picture where I will say if a body has more mass, it induces more curvature in the space-time fabric. A 2D representation is shown in this figure. Then I can predict how the other bodies will move purely geometrically in this space-time curvature. That will then replicate what Newtonian gravity gives me in a particular regime. Right? So Einstein's theory of gravity is a higher level theory where if you approximate in approximation that the masses aren't that heavy, you get Newton's theory back. And general theory, of course, is ubiquitous now. It led to so many predictions. Every single prediction has been realized since then. You might think general theory of relativity is extremely esoteric and it's about the entire universe. Who cares about space-time curvature in our daily life? You need to, because it's so important that, for example, if the software within your cell phones does not include the corrections due to general theory of relativity while calculating your position with the GPS satellite, you will be a few tens of meters off, right? So if you want your call a Swiggy fellow to come and deliver food to your place, he will deliver it a few kilometers away instead if your phone did not account for general theory of relativity correction. So it is in our lives in a much bigger way than you think. Now, that of course, that put together with expansion, etc., told you that the universe must have been much smaller in the past, and now we know that we say that it started in what we call the Big Bang, 13.7 billion years ago, where the universe was as if at a singularity, where as if it had zero radius but infinite density, which of course is an approximation given a current understanding of physics. But we know that it then expanded at an enormous speed called inflation, and it's been expanding ever since. And as it expanded, the incredibly hot matter, radiation, etc., separated out, and the matter then came together to form galaxies, which we know. The fact that the universe started with Big Bang and it's billions of years old again is something all of us or school students now take for granted. They know, yeah, of course, everybody knows the Big Bang, but again, it took decades and years of conflict, of argument, of difference of opinion between scientists to finally understand, to finally come to the conclusion that this is indeed the right picture. Okay. Now, another big prediction of Einstein was clearly that black holes exist. And again, Einstein did not believe this. So, black holes, existence of black holes, as well as the fact that the universe is expanding, were ideas that are too big for Einstein, right? But now, of course, we know that black holes exist, and famously, Roger Penrose was given the Nobel Prize for proving the existence theoretically. And Andrea Ghez and Genzel were given the Nobel Prize the same year for observationally proving that there is a black hole in the center of our own galaxy. Right? Now, this is of course a direct prediction of general theory of relativity, and you need to understand general theory of relativity in order to understand black holes. And of course, black holes are also now the terrain of further theories like quantum gravity and so on. We know that the black holes form when really massive stars more than 8 times as massive as the sun, explode, and the core of that massive star contracts to form a black hole because there's nothing else holding it in place. And these black holes, you also know, can merge and form massive black holes. Right? On the bottom left is a very, very famous picture of what looks like a medulla. It's basically the first direct image of the shadow of a black hole, the center of a nearby giant elliptical galaxy called M87 in the constellation Virgo. This photo, I'm sure you all seen, came in the front page of every single newspaper around the world. So the fact that black holes actually exist, black holes are not just a mathematical abstraction, but they physically exist, however weird and strange they could be. And that we also know how they are formed was the next big idea. And that's again related to Einstein's theory of gravity. Right. Now, I said that we talked about the Big Bang and we said that the universe is expanding ever since. And as it expands, it cools, of course, and then the extremely hot gas and radiation can separate, and then the extremely hot gas can then start cooling and clumping due to its own gravity. Because as it cools, the pressure it has can no longer push against its own gravity, and will start clumping together due to mutual gravity and form structures. These structures will then clump with other structures due to their gravity, become even more massive objects, and then it builds up and builds up and builds up till you form present day galaxies. Okay, so we now know, we don't understand where galaxies came from. If we cannot say, because people thought galaxies must be existing forever because they're massive objects. But if the universe had a beginning, galaxies should also have a beginning, and we now understand how galaxies were produced from this initial soup of radiation and matter in the Big Bang, after Big Bang, and how the structure developed. On the left side is an extensive computer simulation, which actually takes the ingredients of what we know just after the Big Bang, puts them together, churns them in the computer, and then after the half a billion years, you can see galaxies forming in the simulation. So we know what they have, we know what they do, and equally importantly, we also now know that almost every galaxy has supermassive black hole at the center. Remember, massive stars, when they explode, will form black holes whose mass is roughly 1 to 3 times the mass of the sun. But then these galaxies have black holes which are, for example, our own galaxy has a black hole which is around 4 million times the mass of the sun. The M87 galaxy, whose black hole picture we imaged and I showed you before, has black holes 1,000 times as massive. How do you build these supermassive black holes is still not understood really well. But that's again is the next big idea. The next big idea that ties all this together is gravitational waves. Again, Einstein's theory of general relativity predicted gravitational waves. Einstein knew that they should exist, but he thought they'll be too faint to detect, and everybody thought they'll be too faint to detect, till at last LIGO did detect it a few years ago. And the top left, of course, you see this famous prediction, the detection signal from LIGO, Hanford, LIGO, Livingston, from an event where two black holes formed from stars, when orbiting each other due to mutual gravity, and then they ultimately merged and formed a giant black hole with the less mass than the sum of the two masses. The difference in mass is given as gravitational radiation. And now we know that the massive stars form very small massive black holes. We know that there are supermassive black holes in center of all galaxies, and how we get from one to the other is probably where LIGO is going to fill in where it says that black holes, now we have evidence of black holes merging with other black holes to form bigger black holes. And the idea is we do it again and again and again, you get to supermassive black holes, right? So that is the idea of black holes. The last two ideas is that we now, again, Copernican principle, we're not special. We thought we are special in so many ways. And we thought that we know what matter is made of. It's made of protons, electrons, neutrinos, etc., photons, etc., etc. But then we now know since many decades that's not true. Most of the matter, by matter I mean that which has mass, or that which can have a gravitational influence. Let's put it that way. Will also includes photons. Is actually something we don't know, not know anything about, right? We only know 39% of the total gravitating mass of the universe, which we know is made of protons, electrons, baryons, leptons, photons, neutrinos, the standard model of particle physics. 63% of all the gravitating matter in the universe is made of what we call dark matter, because we have absolutely no clue what it is made of. That is a big revelation again, and people still contest this. But that's something we now have enormous evidence from some 15-20 different ways of looking at the universe that there must be dark matter, because we see unknown influence on the unknown gravitational influence on other objects. Remember, Neptune was the first dark matter ever known, but Neptune we found out was a planet. This dark matter we do not yet know what it is. To make matters even worse, most of the energy in the universe also we do not know what it is. So the atoms, the electrons, protons, baryons, leptons, and the dark matter put together is around 30% of all the energy density of the universe. Almost 70% of the energy density of the entire universe is what we call dark energy, because we do not know what it is. We know it's causing the universe to accelerate. Okay, so we know that the universe is accelerating more and more, and that is due to this dark energy. We still do not know what it is made of and what causes it, what is this nature of this dark energy. Okay, so all of these are now open problems in astronomy. I'm going to end now. Again, I keep mentioning the Copernican principle again and again because I think it's important. So Carl Sagan said that we find that we live on an insignificant planet of a humdrum star lost between two spiral arms on the outskirts of a galaxy, which is a member of a sparse cluster of galaxies tucked away in some forgotten corner of a universe in which there are far more galaxies than people. And I think what we have done in the last 1.5 hours, start from the insignificant planet and move to the entire universe. And I showed you how every single word in this sentence was due to a big idea in astronomy. It was a revolution in itself. And the Copernican principle says that, no, if you think we are very special in some way, the universe has a habit of coming and telling you that is not true. However, let me also end with this. There's only the one Earth we have, and for us, the Earth is special. For us, the Sun is special. And in astronomy, somewhere something incredible is always waiting to be known. And I'll stop.
Yeah. Any questions? Or some, if not related to directly to the whatever you have shown, anything would you like to know related to these small developments? You have spoken about milestones which are in the great ideas in astronomy. So we have seen the photographing of black hole.
So what we can do is, since each of these slides is a talk by itself, let's not get questions on topics specifically. What I would like to do, maybe you can ask them, what among these do people think is their favorite big idea? Like what appeals to them the most? What for them is, oh my God, this is the most amazing fact in the entire series of facts. So what do people think?
Yeah. So, among all these ideas, which you feel is more exciting? That's what is.
Personally, what did you feel like? Oh my God, this is an amazing idea, which is indeed a revolution in thinking. Yeah.
Something mind-boggling. The first thing is that we see that the way actually discovered that our planets rotate or revolve around the sun in an elliptic orbit. That is a marvel. Though we take it as a given fact to us, but it took 16 years for our planet to go on, getting this perfect circle and ultimately zeroing on an elliptic oval curve. So this is a very revolutionary discovery actually. So that is one thing. Then you have seen other things also which he has proved. So
So what we can do, Jayant, is just ask people to just say what their favorite big idea is.
I think you can do one thing. See, you instead of just maybe speaking out first itself will be difficult. Maybe for 2-3 minutes let them write down. Let them.
Sure, sure.
Some key points you can just recap whatever is said. At least 2 or 3 points or things which you felt is really you felt something good about it, something very spectacular. Spectacular, how do we feel is that something which we could not predict, but it has been discovered. That is something spectacular, which we will not imagine, isn't it? In fact, I think as somebody said in the morning, from flatness of Earth to a spherical Earth, that is something which is not in our common sense. We don't see a spherical Earth standing on the Earth. So that is an indirect evidence. So in that way, so we come out which you can. So I think that take 5 minutes, write down some of these which are something we have seen about photographing black hole, galaxy structure, so many galaxies in one picture, going beyond and covering the universe in various multiple wavelengths. Now that is quite interesting. What you can't see, you are photographing and you are trying to analyze that. So you are seeing something in the visual, you are seeing something that's much larger in value. So then you are reconciling these two facts and finding out why it should be like that. So when we say to kids what it is all about, they just they can't comprehend. They're very junior level, in class 5, 6, and they are learning about a lot of things. So in fact, when you say about Earth and people standing on the surface, so I am standing on one place and somebody just and people to that is standing upside down. So we are all standing on the top. So these are all very counter our day-to-day experience that is countering that. So something like that. So
hello, sir. My
Yeah,
name is
hi.
Rajila, teacher in Bali Devan School, Perunduki. Sir, you shared a lot of ideas. Actually, all these are beyond our imagination, some of the ideas. What I would like, basically, I'm a chemistry teacher. You shared a lot of ideas about matter in space. Actually, I would like to know more about the composition of elements in stars. You pointed the presence of even buttons for carbon 16. Like that, actually, what I think is nuclear fusion is hydrogen atoms combine to form helium. Then, how all these compounds, carbon compounds, how do they I would like to know about the composition.
Yeah, I got it. Yeah, thanks. I think that's a good question because I think I didn't make that distinction very clear. So good thanks for bringing it up. The nuclei of elements more massive than hydrogen are all produced inside the stars, right? And these are nuclei. Remember, nuclei are made of protons and neutrons, and then they can combine electrons later on outside the star. Outer layers of star are slightly cooler, they can combine electrons and form atoms. Now, chemistry is to do with atoms, not nuclei. Right? Nuclei is nuclear physics. Right? So, the two aspects. Nuclear physics is about how nuclei are produced, heavier nuclei are produced in the centers of stars due to nuclear fusion. Like, hydrogen, helium, lithium, beryllium, carbon, nitrogen, oxygen, etc. The nuclei, right? Chemistry is when they combine electrons and form atoms and molecules, and then how they interact with each other. Now the chemistry does not occur in stars. The chemistry occurs in colder regions, obviously, because the sun, even the sun's surface is 6,000 Kelvin. At 6,000 Kelvin, you're not going to have any chemistry. Almost all atoms are ionized multiple times, right? But then the stars have to come from somewhere. How are stars form? You will get to know later about this. Stars are formed from giant clouds of gas which exist in the galaxy and in all galaxies. These clouds of gas will then at some point parts of this gas cloud will start condensing out of their own self-gravity, and as they condense and they come closer and closer to each other, they'll become hotter and hotter and hotter because more gas connects, and then it gets hotter, and then it gets more massive, then its gravity increases, it can attract more gas, it will become more massive, it will get more hotter and so on. Ultimately it forms a star. But the gas it was born out of is fairly cold. Okay. And that fairly cold gas can be in atomic form or in molecular form. If the atomic gas is even colder, then it will form molecules. And how does it form? And that happens because there is also dust in the Milky Way galaxy, all galaxies. I didn't touch about that, right? So dust is formed when it's colder, and then the chemistry forms on these dust grains. So things like Buckminster fullerene, etc., are formed on the dust grains or on particles in these molecular clouds, which are shielded from ionizing radiation from the stars, so they are opaque. So if you remember, let me just put it up. Yeah, if you look at the bottom left figure, that's an image in the optical from a Hubble Space Telescope, a very famous star-forming galaxy called the Eagle Nebula, and it's also called the Pillars of Creation. Right, the bright emission is coming from the gas, but then the darker part is basically thick gas with dust, and the dust is absorbing all the optical light from coming out. That's why it's dark. Okay. Now inside these dark regions are basically dust and molecules, and therefore it's also very cold. It's only a few tenths of Kelvin as opposed to star's surface is 6,000 Kelvin, right? And the bright emitting gas is probably around 100 Kelvin, but then the dark much more than a few hundred Kelvin. But then the molecular gas inside these dark dust clouds will be a few tens of Kelvin, if not a few Kelvin. And there you can have chemistry happening, complicated chemistry happening, and this is not gas phase chemistry. Gas phase chemistry doesn't produce such complicated molecules usually. This is chemistry on the surface of grains, so it's catalyzed by the grains. You can form ices, and it can be and there's ice phase chemistry and so on. So these molecules are formed in the dust clouds on the surface of grains and dust. So that is the chemistry part, and the nuclear fusion is the other part inside the center of stars. I hope I made that distinction clear.
Okay, sir. Thank you.
Yeah.
Anybody else?
Hello, sir. I'm Risha.
Yeah, hi.
Sir, can you please explain about the usual stages of stuff?
I could, but then you have to wait for that. You have to be here for half an hour more. So I think is there a talk on it later?
The division of stars as such, there is no session. Maybe you can briefly,
Okay, I'll condense a few billion years of evolution into 1 minute, but then maybe Jayan can see if somebody can kind of do a small presentation on that later. So in very, very short summary, excluding all complications, when galaxies form, they form out of gas, and then this gas can then become the more thicker and denser and form molecular gas, and at some point they can then start condensing due to self-gravity in small pockets, and they become hotter and hotter. As they become hotter and hotter, then they become more and more massive and hotter, and then they keep growing. At some point, the center of these condensations become hot enough, the nuclear fusion can start. Let's say at least 10 million Kelvin. Once nuclear fusion starts, you get a star. The star that starts shining brightly. It then evaporates and pushes away all the gas around it from where it forms, so you can see it freely after a few 100,000 years. And some of the remaining gas which condensed into forming the stars will then form planets around it. Now this star will start burning a proton, will do the PP chain reaction, will fuse 4 protons to form helium initially. And what it then does afterwards depends on how massive the star is. Okay? So stars as massive as our sun, for example, once almost all the hydrogen in the core, all the protons in the core, end up fusing to become helium. and then almost all the core is entire helium. The outside part is all hydrogen. The helium, then it doesn't get hot enough for the helium to fuse to something else, and then it becomes what's called a planetary nebula, where the outer layers are gently puffed out into a large gas cloud. And the center becomes what we now call as a white dwarf. Okay, a white dwarf is a very strange kind of object, and you might have heard of white dwarfs in the connection with Chandrasekhar, but I won't go into that. Stars which are a bit more massive than our sun, let's say up to 3 times more massive than the sun, what happens is that the core can contract even more because much more massive, and the helium, they get hot enough for helium to start fusing into carbon, nitrogen, oxygen, etc. Okay, and then you produce carbon, nitrogen, oxygen, maybe fluorine, and so on. And then at each stage it becomes hotter and hotter, and then you can have one more level of fusion to a higher element. At some point, it can no longer again become hot enough to sustain nuclear reaction. Then its gravity will take over, and then the center will collapse to form what is called a neutron star, where instead of having protons and electrons and plasma, you will have completely it's essentially one huge nucleus. You get a 10-kilometer diameter nucleus, which is of enormous density. Outer layers then explode out in the supernova, into form of supernova. It's a huge explosion, which you can see from other galaxies very clearly. And this explosion, and even the planetary nebula explosion of a star like a sun, is what then puts back. Remember, the nuclear fusion has created heavier elements like carbon, nitrogen, oxygen. Now they need to get out into the gas to form new stars, right? And therefore, these explosions then take this matter generated in the core, which is heavier, like other heavier elements, and puts them back into the gas, which then form new stars later. Now, stars which are even more massive than even 8 times as massive as the sun, the center cannot hold, as famously said by Gordon, and ultimately it will keep fusing heavier and heavier elements, phosphorus, sodium, carbon, etc., etc. Ultimately, it will get to iron, and then it can no longer fuse iron because the binding energy per neutron of iron is highest. Once it's come up to iron, then there will be a catastrophic explosion with even brighter supernova, and the center will condense to form a black hole because nothing else preventing it from becoming a black hole anymore. There's nothing opposing the force of gravity. And the surrounding outer layers of the star, which now has elements up to iron mixed in them, will then explode, putting these elements out into space. Now, the elements which are higher atomic number than iron are created during this explosion, and those are also put back into space. So the final products of stars are either basically a white dwarf for stars like a sun, a neutron star for stars which are, let's say, up to 3 times as massive as the sun, and black holes for stars which are much beyond. But there's a continuous cycle of this happening, and because, for example, we have carbon on Earth in our bodies, now it means a sun must have formed out of gas, which must have come out of a much more massive star. Otherwise, there's no way we can get carbon in our solar system. So a star must have existed earlier before the sun was created, which should have been more massive enough to create carbon, nitrogen, oxygen, phosphorus, even iron, right? And even heavier than iron because we have uranium and so on on Earth. So in a supernova, and that gas with all these heavy elements must have then gone up, cooled much later, become a molecular cloud, and then form the sun and the solar system, so that we have those elements in our bodies now. That's like a 2-minute summary of stellar evolution.
Yeah, I think maybe possible sometimes we can have a better conversation about state by state.
Yeah.
It's quite interesting, but it requires quite elaboration with visuals. I think you will appreciate. But the one thing I think is that you can try. I have seen many things. It's really difficult to actually make them understand that our sun is a star. So,
yeah.
How I think from teacher side, better clear how they can.
Which is why I specifically put that as a big idea.
Yeah, it's a big idea because sun we see every day rising and setting, red color, this and all, and stars in night we see them the small dots in the sky, and suddenly we see our kids and see our sun is a star. Now it's not inside. So
yeah, it is a very big idea, and there's a physics story. I mean, every slide I showed can be made into a 1-hour talk about the physics and the history related to that. So we went through a lot in 1.5 hours. But I don't apologize for that. Big ideas are big for a reason.
So I think before you deliberate on that, I would like to ask some teacher. I think this is the question most of us in teaching classes fine. Somebody or the other might have asked that it's difficult for them to believe that sun is a star. Now, how actually, if you have faced this situation, what did you do? How you try to convince the student? Yeah, some ideas. Usually, actually, we try to, if we have something quite interesting, it's good.
Also, Jayant, you had asked them to write down a few points earlier, right? Do they want to kind of read them out?
I think that since they were listening to you,
Okay, fine. I think this conversation will continue over the next 3 days over lunch and dinner and so on.
so, okay, before they were thinking, what do you feel is the best way to explain that the sun is how to convince a class, say 5 or 6 person, a student of class 5 or 6 level, or middle school level, that mostly the small kids, it's very hard to imagine, make them imagine that sun is a star. So how do you, what is the best way to illustrate that? And then we can discuss sometime, we can spend some time on it.
Yeah, it's not easy. None of these ideas are easy. Okay, and none of these ideas are easy to believe in or to convince people without a lot of proof and data and arguments. Right? None of these ideas are obvious at first sight. If you just go about your daily life, none of these ideas are obvious to you. Right? All of them are counterintuitive in some sense. Right? And I think one of the ways you can convince them that sun is a star is to kind of talk about distances. And you can do practical demonstrations like you say, okay, if I have the sun and the earth as two balls here, where do you think the nearest star will be, right? And then you tell them it's going to be a few kilometers away, and then that tells you the distance. Then you say, okay, if you take the sun and then put it a few kilometers away in this scale, how do it look? So you're going to talk about distance versus size in that sense, but then maybe within the city, use a city as a scale, and then convince them that if you take a small, very, very faint star, very, very far away, and then bring them as close as the sun, it will indeed be as bright and as big as the sun is. I think that's one way to do it. But then it's difficult. I mean, it's difficult at the fifth standard level. 6, 7, 7th, 8th is fine, right? So I think the best way to do that would be to tell them, and also use other examples. Like for example, you say you can see a light from a faraway hill, right? And then you have a candle here, and they're both equally bright. But then how far? But then you have to how far away is that? So should that be, or how brighter is that compared to the candle? And why do they appear the same brightness? Because it's so far away. And the concept of how far away should the object be to be so much fainter, and therefore than what you have in front of you. If you understand that concept through examples around you, then you can then say same principle applies to why the sun is so bright and outside bright, but the stars are not, but they're comparable in size and shape actually. So that's one way to do it. Yeah, but they're not. This all require a lot of ingenuity by teachers to kind of convey it in a way which kids can relate. It's not easy. I just want to convey it to the teachers here first. Yeah.
You told me in the discussion that stars are powered by nuclear fusion. So fission and fusion is the combination. So how do you?
Yes, the fusion is when smaller particles combine to form a bigger particle. That's fusion. Fission is when a larger particle decays later to form a smaller particle. Right. So so all of this is nuclear fusion. In stars, it's nuclear fusion, where smaller nuclei come together to form to merge and form bigger nuclei. Now, if the product they form is unstable, like for example, supposing during an explosion of the star, which is very massive, in the atmosphere, the ion will absorb neutrons coming from inside and form maybe uranium or something, right? That uranium will then radioactively decay in its way to form, and that will be nuclear fission. But inside all stars, what is powering it is nuclear fusion, where smaller nuclei come together, merge and form a bigger nucleus. In the process, there is a deficit of energy emitted as photons and neutrinos. That's always the case.
And one more question, since they are not asking, we also might know that. When we say about a big idea, we also say about the expansion of the universe, and we say in terms of redshift and all those things. But then the question comes from the student that, see, our universe is into them. So they are expanding, you say that they are expanding, because there is nothing beyond. Then we give an analogy that take a balloon and put some two spots and it moves out. Then again the question still remains actually. It moves about, that is fine. But then how from that they are expanding? Space is getting created, it's a concept. How do you actually
Yeah, it's not easy, and I think beyond, see, I mean, these at some point, if you take more complicated concepts, then you cannot explain them without mathematics. You can only give analogies. Okay, so this balloon thing is an analogy. The other analogy people use to explain expanding universe is that if you want to make a cake, you have a small, you put dough, a batter, and then you put cake, and then you have all these raisins in it. And as the cake expands in the oven, the cake itself, everything in the cake expands, and then the raisins also move away from each other. They seem to be moving away from each other because the entire space inside expands. Right? That's the other analogy you can give. You can only give analogies, and I don't think that's beyond the point. You can only get so far with qualitative analogies. But these are the two examples I keep hearing often. And if they ask you, what do they expand into? The answer, of course, is that they don't expand into anything. The entire space is expanding. And at some point, they just have to take it as it is and understand it at a deeper level when they read more physics. But so there's a limit. There is a limit to how much you can explain qualitatively, especially when it comes to things like general relativity and so on, which are highly mathematical and also highly counterintuitive. So you can only, but then one thing. So that is there. But one thing I would like to stress is that when we do this, we have to keep mentioning that it's only an analogy, because a lot of times I find that we use these analogies and metaphors very freely. And then the students believe that that's how things are, right? They think, okay, we're actually living in a balloon. Right? So I think it's important to use analogies, but it's equally important to tell them this is only an analogy and not to take it, not to take it literally. And I think that's again something we need to do as teachers. But that's something I see a lot of as well. People confuse the example for the real thing. But I think beyond the point, I think we can only go so far with these examples.
I have one question. I have come to that question. So we have given one question here for them to as a pre-test. So in that actually there is a question on phases of the moon. Now in the children's book, especially in class 5, 6, 7 book, we have a sun on one side. I don't know, it may not focus. We have the sun on one side and we have the earth and one circle showing moon at say 45 degrees. At each point we draw a few circles, and then we show that this is it. Now the thing is that you have drawn phases directly on the top of. Now in your picture it is shown the phases are curved, but when you draw a geometric figure, it just shows a small slice. The curvature is imagined. That actually how it is coming, that we can, when we see from a three-dimensional point of view, or when we see with a focus light and see this, that is easy to comprehend. But from a two-dimensional picture, making the student understand that it forms a crescent, I think it's better the imagination too far. What do you feel about it?
Yeah, so that's where all these teaching aids come in, right? I mean, there's only so much you can do with 2D. But then phase of the moon is something everybody has misconceptions about, and I saw from the answers some of the people here provided that there are misconceptions. Not everybody got them right as well, even in this audience. And I think, but there's something everybody should know, because something you should see in the night sky, but we don't look up in the sky at night, right? We look down on our phones, unfortunately. But then I think now every textbook in school actually has an exercise where the students are supposed to look at the moon and then draw it on, that's how it looks like. That they don't do, but that's a very nice way to do it. The other thing, like you said, is to have 3D. So, for example, what we do a lot is that if you go to a school ground at night, then you actually have a light, and then you ask everybody to sit together in the center like the earth, and you ask someone to hold a big ball and move around them, and they can actually see for themselves physically that the shape of the crescent is curved, right? That's one thing. Other thing to do is, especially for things like these 3D three things which are in 3 dimension, but you see in 2 dimension. A lot of computer simulations available. Just for the face of the moon itself, I gave an entire talk on the face of the moon at some point, some time ago to teachers, where I extensively used a simulation software which is online, which you can do like this, you can look like this, you can go outside, you can do all this, and then you can play with your mouse cursor, and then you can look at it yourself and then figure out what it is like. So a lot of these tools available, and I think the important thing, and I think that's something the OAE India Center also is looking at, is that sometimes people like us who know this very well do not appreciate the kind of misconceptions people will get when they look at a 2D picture of a 3D phenomenon. For us, when I look at the 2D picture of face of the moon, in my mind I have a 3D picture because I've done this like a million times, right? Whereas if we expose it to students for the first time, we kind of don't appreciate that because we're used to it, and therefore a lot of teacher training workshop like this hopefully should also bring up the various misconceptions students will have when encountering this for the first time, and therefore how do you attack those misconceptions using other teaching aids like role-playing games, things to do physically in the playground, animations, simulations, hands-on activities, and so on. So I would look at it that way in a more pedagogical setting.
Yeah. We were discussing about 2 dimension and 3 dimension. Instead is popped up into my mind.
Yes.
Is there any thought about dimensions in our universe, or is it just 3 dimensions?
As far as all the evidence we know is that our universe is 3 dimensions of space and 1 of time, and put together is 4 dimensional space time. Certain certain hypothetical theories like string theory demand around 10 dimensions, and some of them will be rolled up so tiny you won't experience them. But those are right now hypotheses or things people put forward. There's no evidence for any such thing currently at all. Is it time for all your lunch, Jayant? Are they hungry?
Anyway, just last thing that he said about misconceptions. So maybe we can do a small exercise. It isn't that can you just write down at least 1 or 2 common misconceptions which you face with your
Yeah, that will be a very useful exercise. And then Jayant, you can have a session where you discuss those misconceptions with them later this today or tomorrow. That'll be very useful. Exactly. Because even things like eclipses, phase of the moon, you might explain extremely well in your class, and then the student will ask you a question, and you were like, "Where did that come from? However, did you get that weird idea?" And we don't realize how they interpret what you said in a totally different way. And I think those misconceptions are what we need to address in designing our next syllabus and next course curricula and so on. So that'd be a good thing to do. Yeah. But this talk of mine I know covered a lot of ground. The idea of this talk was not to make you understand everything, or not to make you understand nuclear fusion, chemical evolution, Big Bang theory, dark matter, black holes, everything, not at all. The idea was for you to understand that the history of astronomy has come with huge leaps of imagination and changing our perspective of the universe, motivated by observations, motivated by theory, and that each of these leaps were counterintuitive at that time, which now we then take for granted or we now know is obvious. And when you teach students about anything, not just this, anything at all, it's good to keep in mind that those big ideas which for us is obvious are still new for a 10-year-old. Right? The fact that the earth is round or earth spins on its axis is known for 2000 years, and we all know it for however many years we've been living. But then for a 6-year-old, it's still as new as it was for people 2000 years ago, and therefore we can't take that for granted, but try and find ways to explain this big idea. So I think that was in some sense what I wanted to convey. That each of these big ideas might seem obvious now, but they were highly counterintuitive and changed the way people looked at the universe or looked at themselves. Right? So I think I'll end there. I think that's a lot of things to throw at you in one sitting. So.
I think,
Okay.
yeah. So anything else? Anybody? So we can do, I think, maybe last day when we meet again for our conclusion, we can ask people that how, if anything new into that, we can discuss on.
Sure. Yeah. And also these things you wrote down just now, you can keep it and put it in a Google Doc, and I can take a look at it later, and we can see how we can work with you after this teacher training workshop is over, maybe through the WhatsApp group form or so on, and then address some of these issues over the coming weeks or months.
So that is a, see, it is not only that our discussion or announcements will be there. Basically, to interact and interchange. Somebody will put up a question among you itself, somebody will answer, or among you, we are all there in the group. He is also there, others are also there. So if you put up a question, it can be answered by somebody among the faculty, somebody among your other colleague teachers, and others also. So the thing is that this exchange of ideas is what makes these types of programs more fruitful instead of passive listening. So that's what we will try to inculcate during this year, following that also the group will remain for some time, so we can go on discussing. I think with that, I think we can end the conclude this today's now session, because after this at 2 o'clock, some other speaker is going to come for sun. We have today's 2 session on sun and sun observation, followed by solar system. So I thank Dr. Mohan for spending his time with us and giving us a good talk on advances and the big idea of astronomy. And thank you again. And again, we'll meet again on the last day. I'm absolutely informed.
Yeah, and wish you all a really nice workshop, and hope you all have fun and learn a lot of stuff. So, thank you. Bye.
Yeah.